Welcome to Whispering Atom, where the quiet mysteries of the cosmos unfold like gentle whispers in the darkness. I'm here with you tonight to explore one of the most beautiful and constant connections between Earth and the vast universe beyond, the gentle, eternal rain of cosmic dust that falls upon our world every single day. As you settle in wherever you are, let me know where in the world and at what time you're listening. Are you nestled in a comfortable bed with soft pillows supporting your head? Perhaps you're in a cozy chair by a window where you can see the night sky. Or maybe you're lying on a couch, wrapped in your favorite blanket as the day's activities finally come to rest. Tonight, we're going to discover something remarkable about the very air around you, the ground beneath your feet, and even the water you drink. We're going to explore how particles that began their journey in distant stars, in the hearts of comets, and in the vast spaces between planets, eventually find their way to Earth and become part of our world in ways both subtle and profound. These cosmic visitors arrive silently, constantly, bringing with them stories of the universe that stretch back billions of years. But don't worry about grasping every detail as we journey together. Let the ideas flow over you like a gentle stream, carrying away the tensions of the day. Some concepts will settle into your mind immediately, while others will drift and float until they find their perfect place in your understanding. The goal tonight is not to memorize or analyze, but simply to marvel at the quiet connections that bind us to the cosmos. Now, get comfortable. Adjust your position, pull that blanket a little higher, and let your breathing slow to match the peaceful rhythm of discovery. Take a slow, deep breath in, and as you exhale, feel yourself sinking deeper into this moment of quiet exploration. We're about to embark on a journey that begins in the far reaches of space and ends in the most intimate details of your daily life. The universe is constantly sending us gifts, not dramatic meteors or brilliant comets, but something far more subtle and beautiful. Every day, every hour, every minute, tiny particles of cosmic dust settle gently onto our planet, carrying with them the chemical signatures of distant worlds and ancient stellar explosions. These particles are so small that you've never noticed them, so light that they drift down through our atmosphere like the most delicate snow, yet they carry within them the story of the universe itself. Are you ready to discover what really happens when dust from space lands here? Then let's begin this gentle exploration of our cosmic connection. Right now, as you rest there in the comfort of your chosen spot, something extraordinary is happening all around you. It's so gentle, so quiet, that it occurs completely without your awareness. Yet it's one of the most constant and beautiful phenomena occurring on our planet. Above you, invisible to your eyes, tiny particles of dust from the far reaches of space are drifting down through the atmosphere, settling onto the Earth with the soft persistence of the most delicate rainfall. These cosmic visitors have been arriving for billions of years, long before the first life appeared on our planet, long before the oceans formed, long before the atmosphere we breathe today took shape. They continue to arrive now, as you listen to these words, at a rate that would astound you if you could somehow see them all at once. Scientists estimate that between 40 and 100 tons of cosmic dust settles onto Earth every single day. That's equivalent to the weight of several large trucks worth of space material joining our planet's mass every 24 hours. But these aren't the dramatic, fiery visitors that we sometimes see streaking across the night sky. Those meteors, those shooting stars that occasionally light up the darkness, are the rare, large cosmic travelers that announce their arrival with brilliant displays of light and heat. The cosmic dust we're exploring tonight is far more subtle, far more patient. These particles are so small that they slip through our atmosphere almost unnoticed, each one a microscopic messenger carrying information from the depths of space. Picture, if you will, a single particle of cosmic dust as it begins its final approach to Earth. This particle might be no larger than a grain of pollen, perhaps even smaller, so tiny that it would fit comfortably on the head of a pin with room to spare. It has traveled for thousands, perhaps millions of years through the vacuum of space, surviving temperatures that would freeze any earthly substance solid, enduring radiation that would destroy most materials we know. As this particle encounters the outermost reaches of our atmosphere, roughly 60 miles above the surface, it begins to interact with the thin gases that mark the boundary between space and our world. The interaction is incredibly gentle at first. The particle, moving at speeds that might reach several miles per second, begins to slow down as it encounters the first wisps of atmospheric gases. But unlike the dramatic deceleration of larger meteors, which creates the friction that produces brilliant streaks of light, this tiny particle's interaction with the atmosphere is so gentle that it produces no visible effect whatsoever. The particle continues its descent, gradually slowing as it encounters increasingly dense layers of atmosphere. At 30 miles up, it's moving through the stratosphere, that layer of atmosphere where the ozone that protects us from harmful solar radiation resides. Here, the particle might encounter ice crystals, particles of water vapor, or even other cosmic dust particles that have preceded it in this ancient journey from space to Earth. As it descends further, passing through the layer where jet aircraft cruise at 6 miles up, the particle has slowed considerably. It's no longer moving at the incredible speeds it maintained during its journey through space. Instead, it's now drifting downward at a pace that's almost leisurely, perhaps falling at the same rate as a small snowflake on a calm winter day. The particle continues its gentle descent through the lower atmosphere, the region where clouds form and where weather systems play out their daily dramas. Here, it might become incorporated into a cloud droplet, surrounded by water molecules that have evaporated from the ocean or from a distant forest. Or it might continue its solitary journey, drifting through clear air toward the surface below. During this final portion of its journey, the particle might encounter birds in flight, their wings cutting through the air that carries this cosmic visitor downward. It might drift past the windows of tall buildings, invisible to the people working inside, or float through the updrafts created by the warmth of a city on a summer day. All the while, it maintains its patient descent, bringing with it the chemical signature of the cosmic environment from which it came. Finally, after a journey that began in the depths of space and has taken perhaps hours or even days to complete once it entered our atmosphere, the particle reaches the surface. It might land on the leaf of a tree, adding its microscopic mass to the surface that will eventually process it through the cycle of plant growth and decay. It might settle onto the surface of a lake or ocean, where it will sink slowly through the water to join the sediments that accumulate on the bottom. Or it might land on the roof of a building, where it will be washed by the next rain into gutters and storm drains, eventually making its way to rivers and streams that will carry it to the sea. It might even land on your skin as you walk outside, becoming part of the dust that you'll wash away with your next shower, completely unaware that you've been touched by a particle that originated in the heart of a distant star. The remarkable thing about this process is its absolute constancy. As that single particle completes its journey, millions of others are at various stages of the same descent. Some are just entering the upper atmosphere, beginning their gentle deceleration. Others are halfway through their journey, drifting through the middle layers of air. Still others are just moments away from landing, approaching the surface with the same patient inevitability that has characterized their entire journey. This cosmic precipitation never stops. It continues through day and night, through all seasons, through all weather conditions. When you're enjoying a sunny day, cosmic dust is falling. When you're listening to rain pattering on your roof, cosmic dust is falling through and with that rain. When snow is drifting down on a quiet winter evening, cosmic dust is joining that snow in its descent to the earth below. The dust falls onto every surface of our planet. It settles onto the polar ice caps, where it becomes incorporated into the ice that has accumulated over thousands of years. It falls onto the vast expanses of the ocean, where it sinks through miles of water to the deep ocean floor. It settles onto the peaks of the highest mountains, where it might remain for years before being carried away by wind or weather. It falls onto the leaves of the Amazon rainforest, where it becomes part of the complex ecosystem that supports an incredible diversity of life. It settles onto the sands of the Sahara Desert, where it joins the particles that the wind will eventually carry across the Atlantic Ocean to nourish the forests of South America. It lands on the ice sheets of Antarctica, where it becomes part of the frozen record of our planet's atmospheric history. But the cosmic dust doesn't just fall onto the dramatic landscapes of our planet. It also settles onto the ordinary, everyday surfaces of our human world. It lands on the sidewalks of cities, where it mixes with the dust created by human activity. It settles onto the roofs of suburban homes, where it becomes part of the material that will eventually wash into storm drains and make its way to local waterways. It falls onto the gardens where we grow our food, becoming part of the soil that nourishes the plants we eat. It settles onto the surfaces of cars, where it becomes part of the dust that we wash away without a second thought. It even lands on the clothes hanging on outdoor clotheslines, becoming part of the everyday dust that we encounter in our homes and workplaces. The cosmic dust that falls in urban areas joins with the particles created by human activity. The wear from automobile tires, the emissions from factories, the particles created by construction and other industrial processes. But even in the most heavily developed areas, the cosmic component is always present, always contributing its microscopic mass to the complex mixture of particles that makes up the dust of our human environment. In rural areas, far from the influence of heavy human activity, the proportion of cosmic dust in the overall dust budget is higher. Here, the particles from space mix primarily with natural terrestrial dust, particles of soil lifted by the wind, pollen from plants, spores from fungi, and the countless microscopic fragments created by the constant processes of erosion and weathering that shape our planet's surface. The size of these cosmic particles varies considerably. Some are so small that they consist of just a few molecules, particles that are barely larger than the complex organic molecules that form the basis of life. Others are large enough to be visible under a microscope, complex aggregates of different materials that have been fused together by the extreme conditions of space. The composition of cosmic dust is as varied as its size. Some particles are rich in iron and nickel, materials that are common in the cores of asteroids and in the metallic meteorites that occasionally fall to Earth. Others are composed primarily of silicate minerals, the same types of materials that make up much of the Earth's crust. Still others contain organic compounds, complex carbon-based molecules that are the building blocks of life. Some cosmic dust particles contain water, frozen into ice crystals that have survived the journey through space. Others contain rare elements that are uncommon on Earth, materials that were forged in the hearts of dying stars and scattered into space by stellar explosions. Each particle is unique, carrying its own chemical signature that tells the story of its origin and its journey through the cosmos. The age of cosmic dust particles varies as dramatically as their composition. Some particles are relatively young, perhaps only a few million years old, created by recent cometary activity or by collisions between asteroids. Others are ancient beyond comprehension, particles that have been drifting through space for billions of years, perhaps since the early days of our solar system's formation. These ancient particles carry within them the chemical signatures of the conditions that existed when our solar system was young. They contain isotopes of elements that can tell us about the nuclear processes that occurred in the stars that died to create the materials from which our solar system formed. They are, in a very real sense, fossils of the early universe, preserved in the vacuum of space and delivered to us by the gentle process of cosmic dust accumulation. As you rest there, breathing quietly, you might imagine this invisible rain continuing around you. Above your roof, particles are settling that began their journey in the heart of a star that died before our sun was born. In your garden, if you have one, particles are landing that contain organic molecules first formed in the cold depths of interstellar space. On the street outside your home, particles are settling that were once part of a comet that has been circling our sun for millions of years. This cosmic dust carries with it not just the chemical signatures of distant places and ancient times, but also the potential for new discoveries. Scientists who study cosmic dust particles have found materials that don't exist naturally on Earth, compounds that were formed under the extreme conditions of space, and that can tell us about processes that we can't replicate in our laboratories. They found particles that contain amino acids, the building blocks of proteins, suggesting that some of the chemical foundations of life might have been delivered to Earth by cosmic dust. They found particles that contain diamonds, formed in the shock waves of stellar explosions and preserved in the cold vacuum of space. They found particles that contain isotopes of elements that can only be formed in the hearts of the largest stars, providing direct evidence of the nuclear processes that power the universe. The study of cosmic dust has opened up entirely new fields of scientific investigation. Researchers have developed techniques for capturing these particles in the upper atmosphere, using high-altitude aircraft and even spacecraft to collect samples before they can be contaminated by terrestrial materials. They've learned to identify cosmic dust particles in ice cores, in ocean sediments, and even in the dust that accumulates on the surfaces of buildings and other structures. But perhaps the most remarkable thing about cosmic dust is not what it tells us about the universe, but what it reveals about our connection to the cosmos. Every breath you take contains particles that have traveled from the depths of space. Every glass of water you drink contains molecules that were once part of a comet or an asteroid. Every meal you eat contains elements that were forged in the heart of a star and delivered to Earth by the gentle, constant rain of cosmic dust. This connection is not metaphorical or poetic. It's literal and measurable. The calcium in your bones, the iron in your blood, the oxygen that you breathe, all of these elements were created in the nuclear furnaces of ancient stars and scattered into space when those stars died. Much of this material eventually found its way to Earth through the process of cosmic dust accumulation, joining the material that had already condensed to form our planet. The cosmic dust that falls today continues to add to the inventory of materials available on Earth. While the daily accumulation is small compared to the total mass of our planet, over the billions of years that this process has been occurring, the cumulative effect is significant. Some scientists estimate that a substantial fraction of the water in our oceans may have been delivered by cosmic dust and small comets over the history of our planet. As you continue to rest there, feeling the gentle rhythm of your breathing, you might reflect on the fact that you're literally made of star stuff. Not just in the sense that the elements in your body were forged in ancient stars, but in the sense that these elements were delivered to Earth by the same gentle process that continues today. The cosmic dust that is falling around you at this very moment is part of the same process that helped create the materials from which you are made. This realization can bring a profound sense of connection and peace. You are not separate from the universe. You are part of it, made from it, connected to it through processes that span billions of years and countless light years of space. The gentle rain of cosmic dust that falls constantly around you is a reminder of this connection, a daily demonstration of the fact that Earth and all life upon it are intimately connected to the cosmos. The next time you see dust motes dancing in a shaft of sunlight, you might remember that some of those particles have traveled from the depths of space to reach that moment. The next time you feel the dust that accumulates on the surfaces of your home, you might remember that mixed in with the terrestrial particles are visitors from distant worlds, carrying stories of the universe that we are only beginning to understand. And as you drift towards sleep tonight, you might find comfort in knowing that this gentle cosmic rain continues around you, connecting you to the vast tapestry of space and time, reminding you that you are part of something much larger and more beautiful than you might have imagined. The universe is not a distant, foreign place. It is your home, and it is constantly sharing its gifts with you through the simple, elegant process of cosmic dust settling gently onto our world. Now, as you rest there with a deeper understanding of the cosmic dust that falls around us, let me take you on a journey backward through time and space to discover where these gentle visitors come from and how they begin their long voyage to Earth. Each particle that settles onto our planet carries with it a story that spans millions, sometimes billions of years, and understanding these stories helps us appreciate the remarkable journey that brings the universe to our doorstep. Imagine, if you will, a dying star in a distant part of our galaxy, perhaps a red giant nearing the end of its life cycle. This star, once similar to our own sun, has swollen to enormous size as it burns through the last of its nuclear fuel. Its outer layers, heated to temperatures that would vaporize any earthly material, are being gently expelled into space in a process that will continue for thousands of years. As these stellar winds carry material away from the dying star, they create the first chapter in the story of cosmic dust. The material expelled by this dying star contains all of the elements that were forged in the star's core during its lifetime: carbon, oxygen, silicon, iron, and dozens of other elements that were created through the nuclear fusion processes that powered the star for billions of years. As this material moves away from the star and into the cold vacuum of space, it begins to cool and condense, forming the tiny solid particles that we call cosmic dust. The process of dust formation in stellar winds is remarkably gentle. The hot gases expelled by the star gradually cool as they expand into space, and as they cool, atoms begin to stick together to form small clusters, then larger grains, then the microscopic particles that will eventually make their way to Earth. It's a process similar to the way that water vapor condenses into droplets when it cools, but occurring at temperatures and in conditions that are completely alien to our earthly experience. Some of the cosmic dust that reaches Earth comes from these stellar winds, carrying with it the chemical signature of the star that created it. But other cosmic dust particles have even more dramatic origins. When the most massive stars reach the end of their lives, they don't simply puff off their outer layers like red giants. Instead, they explode in spectacular events called supernovas, releasing in a few seconds more energy than our sun will produce in its entire lifetime. These stellar explosions create shockwaves that race through space at speeds of thousands of miles per second, heating and compressing the material they encounter. In the intense conditions created by these shockwaves, new types of cosmic dust are formed, particles that contain exotic materials that can only be created in the extreme environments of stellar explosions. Some of these particles contain diamonds, formed in the incredible pressures and temperatures of the supernova shockwave. Others contain isotopes of elements that are extremely rare on Earth, materials that can only be forged in the nuclear furnaces of exploding stars. The dust created by supernovas is scattered across vast regions of space, traveling at high speeds and carrying with it the energy of the explosion that created it. Over time, this high-speed dust slows down as it interacts with the thin gas that exists between stars, but it may travel for millions of years before it finally comes to rest or is incorporated into new stellar systems. Another major source of cosmic dust is much closer to home: the comets that orbit our sun in the outer reaches of our solar system. These ancient objects, sometimes called dirty snowballs, are remnants from the early days of our solar system's formation. They consist of a mixture of ice and rocky material, and when their elliptical orbits bring them close to the sun, the heat causes the ice to sublimate, creating the glowing tail that makes comets so spectacular to observe. As a comet approaches the sun, it doesn't just lose ice, it also loses rocky material, creating a stream of dust particles that follows the comet's orbit. When Earth passes through one of these dust streams, we experience meteor showers, those beautiful displays of shooting stars that occur at predictable times each year. But most of the dust released by comets is too small to create visible meteors. Instead, it drifts through space as microscopic particles, some of which eventually make their way to Earth through the gentle process we explored in our first chapter. The dust released by comets is particularly interesting because it contains materials that have been preserved in the cold outer reaches of our solar system for billions of years. These particles carry with them the chemical signatures of the early solar system, providing us with direct samples of the materials from which our sun and planets formed. In a very real sense, cometary dust particles are fossils of our solar system's birth, preserved in the deep freeze of space and delivered to us by the orbital mechanics of these ancient travelers. Asteroids, those rocky objects that orbit the Sun primarily between Mars and Jupiter, also contribute to the cosmic dust that reaches Earth. When asteroids collide with each other, they create clouds of dust that can persist in space for millions of years. Some of this dust eventually spirals in toward the Sun due to various gravitational and radiation effects, and a portion of it eventually reaches Earth. The dust from asteroids tends to be different in composition from cometary dust, reflecting the different conditions under which asteroids formed. While cometary dust often contains significant amounts of organic compounds and water ice, asteroidal dust is typically composed of silicate minerals and metals, similar to the materials that make up the rocky planets of our inner solar system. But the journey of cosmic dust doesn't begin with its creation in stellar winds, supernova explosions, or cometary tails. To truly understand where cosmic dust comes from, we need to go back even further to the very birth of our galaxy and the first generation of stars that began to shine in the early universe. In the beginning, shortly after the Big Bang, the universe contained only the lightest elements, hydrogen and helium, with tiny traces of lithium. All of the heavier elements that make up the cosmic dust we've been discussing, carbon, oxygen, silicon, iron, and all the rest, were created later in the nuclear furnaces of the first stars. These early stars, some of which were much more massive than any stars that exist today, lived fast and died young, exploding as supernovas and scattering their newly created elements into space. The shock waves from these early supernovas compressed the surrounding gas, triggering the formation of new stars from material that now contain the heavy elements created by the previous generation. This process continued over billions of years, with each generation of stars adding to the inventory of heavy elements in the galaxy. The cosmic dust that reaches Earth today is part of this ongoing process, carrying with it elements that were created in stars that lived and died billions of years ago. The journey of cosmic dust through space is influenced by many factors beyond the initial impulse that sent it on its way. The solar wind, that stream of charged particles that flows constantly from our sun, can push dust particles around, altering their trajectories and affecting when and where they might eventually land. The magnetic fields that permeate our galaxy can also influence the paths of dust particles, particularly those that carry an electrical charge. Radiation pressure from starlight can also affect cosmic dust particles. When light from a star hits a dust grain, it imparts a tiny push, similar to the way that solar panels on spacecraft can be used for propulsion. Over long periods of time, this radiation pressure can significantly alter the trajectory of dust particles, sometimes accelerating them, and sometimes slowing them down, depending on their size and composition. The interstellar medium, that thin gas that exists between stars, also plays a role in the journey of cosmic dust. As dust particles move through this medium, they can collide with gas molecules, gradually losing energy and changing direction. They can also accrete additional material from the interstellar medium, growing larger and changing composition as they travel. Some cosmic dust particles become incorporated into molecular clouds, those vast regions of space where new stars are born. In these clouds, dust particles can serve as nucleation sites for the formation of ice crystals and other complex molecules. The dust can also shield the interior of the cloud from harmful radiation, creating conditions that allow complex organic molecules to form. When new stars form within these molecular clouds, they often develop planetary systems, and cosmic dust plays a crucial role in this process. The dust particles in the cloud can stick together to form larger objects, which can then grow through accretion to become asteroids, comets, and eventually planets. In this way, the cosmic dust that formed from the death of ancient stars becomes incorporated into new worlds, continuing the cycle of stellar birth and death that has been occurring throughout the history of our galaxy. The dust particles that eventually reach Earth have typically undergone a complex journey through multiple environments. A single particle might have been created in the stellar wind of a dying star, then incorporated into a molecular cloud, then ejected from that cloud by the formation of a new star, then influenced by radiation pressure and stellar winds, and finally captured by our solar system's gravitational field and drawn toward Earth. The timescales involved in these journeys are almost beyond comprehension. A dust particle that lands on Earth today might have begun its journey when our galaxy was young, before our solar system even existed. It might have drifted through space for billions of years, surviving temperatures near absolute zero, bombardment by cosmic rays, and the gravitational influences of countless stars and other celestial objects. The fact that these particles survive such journeys is remarkable in itself. The conditions of space are incredibly hostile to solid matter. The vacuum of space, the extreme temperatures, the radiation from stars and other sources, all of these factors work to break down and destroy solid objects. Yet cosmic dust particles are small enough and tough enough to survive these conditions for enormous periods of time. The composition of cosmic dust reflects the complex nuclear processes that occur in stars. Different types of stars create different elements, and the proportions of these elements in cosmic dust can tell us about the stellar processes that created them. For example, dust that is rich in oxygen and silicon likely came from lower mass stars like our Sun, while dust that contains elements like titanium and chromium probably came from more massive stars. Some cosmic dust particles contain isotopes of elements that can only be created in specific stellar environments. These isotopic signatures are like fingerprints that can tell us not just what type of star created the dust, but also details about the conditions that existed when that star lived and died. By studying these isotopic signatures, scientists can reconstruct the history of stellar nucleosynthesis in our galaxy, understanding how the elements that make up our world were created and distributed. The organic compounds found in some cosmic dust particles are particularly intriguing. These complex carbon-based molecules, including amino acids and other compounds that are essential to life as we know it, form in the cold environments of interstellar space through processes that we're still working to understand. The discovery of these organic compounds in cosmic dust has profound implications for our understanding of how life might have originated on Earth and whether similar processes might be occurring elsewhere in the universe. As cosmic dust particles approach our solar system, they encounter the solar wind and the magnetic field generated by our Sun. These interactions can alter the particles' trajectories, and they can also modify the particles themselves. The solar wind can strip away loosely bound atoms from the surface of dust particles, while the Sun's magnetic field can trap charged particles and cause them to spiral in complex patterns. The gravitational influence of the planets also affects the paths of cosmic dust particles. Jupiter, with its enormous mass, acts as a kind of gravitational vacuum cleaner, capturing or deflecting many of the larger dust particles that enter our solar system. This protective effect reduces the amount of cosmic dust that reaches the inner solar system, but it doesn't eliminate it entirely. The particles that do make it past Jupiter's gravitational influence are typically the smallest ones, those that are most likely to drift gently down through Earth's atmosphere rather than burning up in dramatic meteor displays. The seasonal variation in cosmic dust accumulation on Earth reflects the changing geometry of our planet's orbit around the Sun. At certain times of year, Earth is moving in a direction that causes us to encounter more cosmic dust, while at other times, we're moving in a direction that results in less dust accumulation. These variations are subtle but measurable, and they provide additional information about the distribution of dust in our solar system. The magnetic field of Earth also influences cosmic dust accumulation. Charged dust particles can be deflected by our planet's magnetic field, while neutral particles pass through unaffected. This selective filtering means that the cosmic dust that reaches Earth's surface may have a different composition than the dust that exists in space around our planet. As you rest there now, breathing quietly in the gentle darkness, you might imagine the vast cosmic recycling process that has brought the elements in your body from the hearts of ancient stars to your present moment. The oxygen you breathe, the carbon in your cells, the iron in your blood, all of these elements were created in stellar furnaces billions of years ago and have been cycling through the galaxy ever since, sometimes incorporated into new stars, sometimes drifting as cosmic dust, sometimes becoming part of planets and the life that evolves on them. The cosmic dust that falls around you carries with it the history of this process. Each particle is a messenger from the deep past, a fragment of the ongoing story of how the universe creates and distributes the elements that make complex chemistry and ultimately life possible. The gentle rain of cosmic dust that we explore in our first chapter is part of a vast network of stellar birth and death, of matter and energy flowing through the galaxy in cycles that span billions of years. This perspective can bring a profound sense of connection and wonder. You are not just a temporary collection of atoms assembled by chance. You are part of an ancient and ongoing process that connects you to every star in the sky, every planet in the universe, every other living thing that has ever existed. The cosmic dust that settles around you is a daily reminder of this connection, a gentle demonstration of the fact that the universe is not a collection of separate objects, but a unified whole, with matter and energy flowing freely from one form to another. The next time you look up at the night sky, you might remember that some of the dust particles settling around you at that very moment began their journey in the light of those distant stars. The next time you feel the dust that accumulates in your home, you might remember that mixed in with the terrestrial particles are ancient travelers that have crossed the galaxy to reach you, carrying with them the chemical signatures of worlds and processes that existed long before Earth was born. And as you continue to drift towards sleep, you might find comfort in knowing that you are part of this ancient cosmic story, that the elements in your body have been on a journey through space and time that spans billions of years, and that the gentle process of cosmic dust accumulation continues to connect you to the vast, beautiful, ever-changing universe that is your home. Now, as you rest there with a deeper understanding of the cosmic journeys that bring dust to our world, let me invite you to follow these ancient travelers through their final moments of arrival, as they make contact with Earth and begin their integration into the complex systems that sustain life on our planet. This transition from the vacuum of space to the rich environment of Earth is one of the most delicate and beautiful processes in nature, occurring millions of times each day with a gentleness that belies the cosmic significance of each arrival. Picture, if you will, the uppermost reaches of our atmosphere, that thin boundary layer where space gradually gives way to the protective envelope of gases that surrounds our planet. Here, roughly 60 miles above the surface, the first cosmic dust particles begin their interaction with Earth's atmosphere. The transition is so gradual that there's no clear moment when a particle stops being a space traveler and becomes an atmospheric resident. Instead, there's a gentle merger, a slow integration that occurs over many miles of descent. As a cosmic dust particle encounters the first wisps of atmospheric gas, it experiences forces that it hasn't felt for perhaps millions of years. The vacuum of space offers no resistance to motion, but Earth's atmosphere, even at its thinnest, begins to exert a subtle drag on the particle. The interaction starts with individual collisions between the dust particle and molecules of nitrogen and oxygen, each collision transferring a tiny amount of energy and gradually slowing the particle's motion. The beauty of this process lies in its incredible gentleness. Unlike the dramatic entry of larger meteors, which create friction hot enough to vaporize the incoming material and produce brilliant streaks of light, cosmic dust particles are so small that they shed their excess energy gradually and peacefully. They don't burn up in the atmosphere. Instead, they simply slow down, gradually matching their speed to the motion of the air around them. As the particle continues its descent, it encounters increasingly dense layers of atmosphere. In the thermosphere, that layer of atmosphere where the International Space Station orbits, the particle begins to interact more frequently with atmospheric molecules. The collisions become more common, and the particle's speed continues to decrease. Yet even here, the process remains gentle, with the particle's temperature rising only slightly as it sheds the kinetic energy of its cosmic journey. The particle's surface begins to interact chemically with the atmosphere around it. If the particle contains iron, for example, it might begin to develop a thin layer of oxidation as it encounters oxygen molecules in the atmosphere. If it contains organic compounds, these might begin to react with atmospheric gases, creating new chemical bonds and potentially forming new types of molecules that didn't exist in the cold vacuum of space. As the particle descends through the stratosphere, it encounters a richer chemical environment. Here, it might interact with ozone molecules, with water vapor, with the various trace gases that make up the complex chemistry of our atmosphere. The particle becomes a tiny laboratory for atmospheric chemistry, providing surfaces where chemical reactions can occur and new compounds can form. The particle's journey through the atmosphere is not just a matter of falling straight down. The complex circulation patterns of our atmosphere carry the particle on a wandering path that might take it thousands of miles from where it first entered the atmosphere. High-altitude winds in the jet stream can carry particles around the globe, while the rising and falling air masses associated with weather systems can cause particles to ascend and descend repeatedly as they make their way toward the surface. During this atmospheric journey, the particle encounters other travelers. It might collide with other cosmic dust particles, creating larger aggregates that combine materials from different parts of the galaxy. It might encounter particles of terrestrial origin, sulfur compounds from volcanic eruptions, salt particles from the oceans, or organic compound from forests and other ecosystems. These encounters can create hybrid particles that combine cosmic and terrestrial materials in unique ways. The particle might also encounter water vapor and become the nucleus for the formation of a cloud droplet. In this case, the cosmic dust particle becomes surrounded by a shell of liquid water, creating a tiny sphere that can grow as it encounters more water vapor. This process, called nucleation, is crucial for cloud formation, and cosmic dust particles serve as some of the condensation nuclei that allow water vapor to condense into the droplets that make up clouds. If the particle becomes incorporated into a cloud droplet, its journey to the surface takes on a different character. It might participate in the formation of raindrops, joining with other droplets to create larger drops that eventually fall as precipitation. In this case, the cosmic dust particle reaches the surface as part of a raindrop, carrying with it the water molecules that surrounded it during its final descent. Alternatively, if the particle encounters a cloud in freezing conditions, it might become incorporated into an ice crystal. The cosmic dust particle serves as a freezing nucleus, providing a surface around which water molecules can arrange themselves into the crystalline structure of ice. The particle might then become part of a snowflake, riding to the surface in the intricate ice crystal formations that make snow so beautiful to observe. The process of snow formation around cosmic dust particles is particularly fascinating because it preserves the particle in a relatively pristine state. The ice that forms around the particle protects it from further chemical reactions, essentially freeze-drying it and preserving its cosmic chemistry until the snow melts and releases the particle into the environment. For particles that don't become incorporated into precipitation, the journey continues as a gentle drift through the lower atmosphere. These particles, now moving at speeds similar to small aerosol particles, are carried by air currents and gradually settle toward the surface under the influence of gravity. Their final descent speed depends on their size and density, with smaller particles falling more slowly than larger ones. The settling process is influenced by the complex patterns of air circulation that characterize our atmosphere. Updrafts can carry particles higher into the atmosphere, while downdrafts can accelerate their descent. The diurnal cycle of heating and cooling creates vertical air movements that can cause particles to rise during the day and fall during the night. Seasonal weather patterns can carry particles from one continent to another, distributing cosmic dust around the globe. As particles approach the surface, they encounter the boundary layer of the atmosphere, that region where the air is most influenced by the presence of the Earth's surface. Here, turbulence created by wind flowing over the landscape can create complex patterns of air movement that can carry particles in unpredictable directions. A particle might be carried up and down repeatedly before finally coming to rest on the surface. The final moments of a cosmic dust particle's journey are determined by the specific conditions it encounters as it approaches the surface. A particle descending over a forest might be captured by the leaves of trees, becoming part of the surface dust that accumulates on vegetation. The waxy surfaces of leaves can trap particles, holding them until rain washes them away or until the leaves fall and decompose, releasing the particles into the soil. A particle descending over an urban area might land on the roof of a building, where it joins the complex mixture of dust that accumulates in cities. Here, it mixes with particles from automobile exhaust, industrial emissions, and the wear and tear of urban infrastructure. The cosmic origin of the particle becomes just one component in the complex chemical mixture that characterizes urban dust. Over the ocean, cosmic dust particles settle onto the surface of the water, where they begin a different kind of journey. Some particles might float on the surface tension of the water, while others sink immediately into the depths. The particles that sink become part of the marine sediment that accumulates on the ocean floor, joining the slow but steady accumulation of material that forms the geological record of cosmic dust deposition. The particles that remain at the ocean surface might be consumed by marine organisms, entering the food chain and eventually becoming incorporated into the tissues of sea creatures. In this way, cosmic dust becomes part of the living systems of our planet, carrying its unique chemical signature into the biological processes that sustain marine life. On land, cosmic dust particles settle onto a variety of surfaces, each of which offers different possibilities for the particle's future. Particles that land on soil might be taken up by plant roots, becoming part of the nutrient cycling that sustains terrestrial ecosystems. Particles that land on rock surfaces might remain there for years or decades, slowly weathering and releasing their constituent elements into the environment. The integration of cosmic dust into Earth systems is remarkably thorough. There's no corner of our planet that remains untouched by this cosmic contribution. Particles settle onto the ice caps of Greenland and Antarctica, where they become part of the frozen record of atmospheric composition. They settle into the deep ocean basins, where they join the sediments that preserve the history of our planet's climate and atmospheric conditions. They settle onto the highest mountain peaks, where they might remain for years before being carried away by wind and weather. They settle into the Amazon rainforest, where they become part of the complex nutrient cycling that sustains one of the world's most diverse ecosystems. They settle into the Sahara Desert, where they join the sand and dust that the wind carries across the Atlantic to fertilize the forests of South America. The process of cosmic dust integration is not just a matter of physical settling. It's also a process of chemical integration. As particles interact with the Earth's environment, they undergo chemical reactions that can transform both the particles themselves and the terrestrial materials they encounter. Iron-rich particles might undergo oxidation, creating rust-colored compounds that become part of the soil. Organic compounds in cosmic dust might interact with terrestrial organic matter, creating new chemical combinations that didn't exist before. The pH of the environment where cosmic dust settles can influence these chemical reactions. In acidic environments, some cosmic dust particles might dissolve more readily, releasing their constituent elements into solution where they can be taken up by plants or transported by water. In alkaline environments, different chemical reactions might occur, creating different products and different pathways for the integration of cosmic materials into terrestrial systems. The biological activity of the environment also influences how cosmic dust is integrated. Bacteria and other microorganisms can interact with cosmic dust particles, potentially using them as sources of nutrients or as surfaces for biochemical reactions. Some microorganisms might even be able to metabolize the organic compounds found in cosmic dust, incorporating cosmic carbon into their cellular structures. Plants, too, can interact with cosmic dust in various ways. The particles that settle on leaf surfaces might be taken up through the leaf stomata, those tiny pores that allow gas exchange. Particles that reach the soil might be absorbed by plant roots along with water and dissolve nutrients. In this way, cosmic dust becomes part of the plant structure, and through the food chain, it eventually becomes part of the animals that consume those plants. The seasonal cycles of plant growth and decay create patterns in cosmic dust integration. During the growing season, plants actively take up nutrients from the soil, including elements that originated in cosmic dust. During the dormant season, decaying plant material releases these elements back into the soil, where they can be taken up by new plants the following season. This creates a continuous cycling of cosmic materials through terrestrial ecosystems. The hydrological cycle also plays a crucial role in cosmic dust integration. Rain and snow wash cosmic dust particles from the surfaces where they initially settle, carrying them into streams and rivers that eventually transport them to the ocean. This hydrological transport can carry cosmic dust particles thousands of miles from where they first landed, distributing cosmic materials throughout the world's water systems. In the ocean, cosmic dust particles become part of the marine sediment that accumulates on the seafloor. Over millions of years, these sediments are compressed and transformed into sedimentary rocks that preserve the record of cosmic dust deposition. Geologists can study these rocks to understand how the rate of cosmic dust accumulation has changed over time, providing insights into the history of our solar system and our galaxy. The integration of cosmic dust into Earth systems is so thorough that it's virtually impossible to find any part of our planet that doesn't contain some contribution from cosmic sources. The air you breathe, the water you drink, the food you eat, all of these contain elements that originated in cosmic dust. The soil in your garden, the rocks in your local landscape, even the dust that accumulates in your home. All of these contain cosmic contributions. This integration is ongoing and continuous. As you rest there now, cosmic dust particles are settling around you, beginning their integration into the Earth systems that sustain your life. Some particles are landing on the roof of your building, where they'll be washed by the next rain into the local water system. Others are settling onto the ground outside, where they'll become part of the soil that nourishes local plants. The remarkable thing about this process is its gentleness and its persistence. Unlike the dramatic geological processes that reshape our planet's surface, the integration of cosmic dust occurs quietly and gradually, particle by particle, day by day, year by year. Yet over the long term, this gentle process has a profound cumulative effect, contributing to the chemical complexity and diversity that make Earth such a remarkable planet. The cosmic dust that settles today joins the vast inventory of cosmic materials that have been accumulating on Earth for billions of years. This accumulation represents a continuous connection between our planet and the cosmos, a daily reminder that Earth is not isolated in space, but is part of a vast network of material and energy exchange that spans the entire universe. As you continue to rest there, breathing quietly in the gentle darkness, you might imagine this ongoing process of cosmic integration occurring around you. The air you breathe contains particles that have traveled from distant stars. The water in your body contains molecules that may have originated in comets or asteroids. The food you ate today contains elements that were forged in the hearts of ancient stars and delivered to Earth by the gentle process of cosmic dust accumulation. This perspective can bring a profound sense of connection and wonder. You're not just living on a planet. You are part of a planet that is constantly receiving gifts from the cosmos, integrating these gifts into the complex systems that sustain life. The quiet landing of cosmic dust that we've explored in this chapter is part of a vast process of cosmic recycling that connects you to the deepest structures of the universe. The next time you see dust settling in a shaft of sunlight, you might remember that some of those particles have just completed journeys that began in the far reaches of space. The next time you feel rain on your skin, you might remember that some of the water in those raindrops condensed around cosmic dust particles. The next time you breathe deeply of fresh air, you might remember that some of the molecules entering your lungs have been part of the cosmic dust that falls constantly around us. And as you drift towards sleep, you might find comfort in knowing that this gentle process of cosmic integration continues around you, connecting you to the vast universe beyond our planet, reminding you that you are part of something much larger and more beautiful than the boundaries of our world might suggest. Now, as you rest there with an understanding of how cosmic dust gently integrates into our world, Let me invite you to explore the remarkable cargo that these tiny particles carry with them on their journey from space. Each grain of cosmic dust is far more than just a speck of matter. It's a microscopic messenger, carrying within its structure a detailed record of the conditions, processes, and chemistry of the cosmic environments from which it came. These particles bring us direct samples of distant worlds, ancient stellar processes, and the complex chemistry of interstellar space. Imagine, if you will, holding in your hand a particle of cosmic dust so small that it's invisible to the naked eye. This particle, perhaps only a few micrometers across, contains within its structure information that would fill libraries if we could decode it completely. Its composition tells us about the star that created its elements. Its isotopic ratios reveal the nuclear processes that forged its atoms, and its molecular structure preserves evidence of the chemical reactions that occurred in the cold depths of space. The most remarkable aspect of cosmic dust particles is their incredible diversity. No two particles are exactly alike, because each one has experienced a unique journey through space and time. Some particles are primitive, relatively unchanged since they formed in the early solar system billions of years ago. Others are highly processed, having been heated, irradiated, and chemically altered by their passage through various cosmic environments. The primitive particles are particularly precious because they preserve the original chemistry of the solar nebula from which our sun and planets formed. These particles contain isotopic ratios that are different from anything found naturally on Earth, providing direct evidence of the nuclear processes that occurred in the stars that contributed material to our solar system. They contain organic compounds that formed in the cold vacuum of space, offering clues about the chemical processes that might have contributed to the origin of life on Earth. Among the most fascinating components of cosmic dust are the organic molecules that many particles contain. These aren't simple carbon compounds. They're complex molecules that include amino acids, the building blocks of proteins, and even more sophisticated organic structures that approach the complexity of biological molecules. The presence of these compounds in cosmic dust suggests that the chemistry necessary for life might be far more widespread in the universe than we previously imagined. The amino acids found in cosmic dust particles are particularly intriguing because they include both the types that are commonly found in terrestrial life and types that are rare or absent on Earth. This suggests that the cosmic dust is not contaminated with terrestrial biological material, but rather that it represents a genuine sample of the organic chemistry that occurs in space. The discovery of these compounds has revolutionized our understanding of astrobiology and the potential for life elsewhere in the universe. Some cosmic dust particles contain water, preserved as ice crystals or chemically bound within mineral structures. This water carries with it isotopic signatures that reveal its origin, whether it formed in the cold outer regions of the solar system, in the atmospheres of distant stars, or in the chemical reactions that occur in interstellar space. The presence of water in cosmic dust contributes to our understanding of how water, essential for life as we know it, is distributed throughout the universe. The mineral components of cosmic dust are equally fascinating. Many particles contain silicate minerals similar to those found in Earth's crust, but with subtle differences in composition and structure that reveal the exotic conditions under which they formed. Some particles contain minerals that are stable only at extremely high temperatures, evidence of their formation in the hot atmospheres of stellar winds. Others contain minerals that could only form in the intense radiation fields around dying stars. Perhaps most remarkably, some cosmic dust particles contain diamonds, not the large, clear crystals prized for jewelry, but microscopic diamonds that formed in the shock waves of stellar explosions. These diamonds are some of the hardest materials known, and their presence in cosmic dust provides direct evidence of the extreme conditions that exist in supernovas. The diamonds often contain trapped gases with isotopic compositions that reveal details about the nuclear processes that occur in exploding stars. The isotopic compositions of cosmic dust particles are like fingerprints that reveal their origins. Different stellar processes create different isotopic ratios, and by measuring these ratios in cosmic dust particles, scientists can determine whether a particle came from a red giant star, a supernova explosion, or the cold chemistry of interstellar space. Some particles contain isotopic anomalies that are so extreme they could only have been created in the most exotic stellar environments. The study of cosmic dust particles has revealed that our solar system formed from materials that came from many different stellar sources. The dust contains isotopic signatures from red giant stars, supernovas, and even more exotic objects like asymptotic giant branch stars and Wolf-Rayet stars. This diversity suggests that the solar nebula from which our sun and planets formed was thoroughly mixed, containing materials from throughout our local region of the galaxy. The organic compounds in cosmic dust also preserve information about the chemical processes that occur in space. The molecules found in these particles couldn't have formed under the conditions that exist on Earth. They require the unique environment of space, with its extreme cold, intense radiation, and near-perfect vacuum. The presence of these compounds in cosmic dust provides a direct window into the chemistry of the cosmos. Some cosmic dust particles contain complex organic molecules that appear to have formed through a process called Fischer-Tropsch synthesis, a chemical reaction that can produce organic compound from simple starting materials under the right conditions. This process might have been important in the early solar system, helping to create the organic compounds that would later become incorporated into planets and potentially contribute to the origin of life. The discovery of fullerenes, soccer ball-shaped molecules of carbon, in cosmic dust has opened up new areas of research. These molecules, which include the famous buckyballs and carbon nanotubes, are incredibly stable and can survive the harsh conditions of space for millions of years. Their presence in cosmic dust suggests that complex carbon chemistry is occurring throughout the universe, creating molecules that might serve as the building blocks for even more complex structures. The metals found in cosmic dust particles also tell remarkable stories. Iron particles often show evidence of having been partially oxidized during their journey through space, indicating that they encountered oxygen-rich environments. Nickel-iron particles sometimes contain traces of other metals that were incorporated during their formation, providing clues about the chemical conditions in the environments where they formed. Some cosmic dust particles contain glass, not the familiar glass we use in windows and bottles, but exotic glasses that formed when hot gases cooled rapidly in space. These glasses often contain dissolved elements that provide information about the composition of the gases from which they formed. The presence of these glasses in cosmic dust provides direct evidence of the rapid cooling that occurs when hot stellar winds expand into the cold vacuum of space. The study of cosmic dust particles has also revealed evidence of secondary processing that occurred during their journey through space. Many particles show signs of having been heated, irradiated, or chemically altered by their passage through various cosmic environments. This processing can modify the original composition of the particles, but it also provides additional information about the conditions they encountered during their travels. Space weathering, the process by which cosmic dust particles are gradually altered by exposure to solar wind and cosmic radiation, creates characteristic changes in the particle surfaces. These changes can be studied to determine how long particles have been exposed to the space environment and what conditions they encountered during their journey. The weathering patterns also provide information about the magnetic fields and radiation environments that the particles pass through. The magnetic properties of cosmic dust particles provide another source of information about their origins and history. Some particles contain magnetic minerals that preserve records of the magnetic fields they encountered during their formation and journey. By studying these magnetic signatures, scientists can learn about the magnetic environments of stellar winds, supernova explosions, and interstellar space. The size distribution of cosmic dust particles also carries information about their origins and processing. Different cosmic environments produce particles with different size distributions, and the weathering and fragmentation that occurs during the journey through space can further modify these distributions. By studying the sizes of particles collected at different times and locations, scientists can infer information about the cosmic dust sources and the processes that affect the particles during their travel. The seasonal variations in cosmic dust composition that reach Earth provide additional clues about the sources and transport of these particles. At different times of year, Earth encounters dust streams from different comets and asteroid families, each with their own characteristic compositions. By studying these seasonal variations, scientists can identify the specific cosmic sources that contribute to the dust we collect and study. The three-dimensional structure of cosmic dust particles, revealed by sophisticated microscopy techniques, shows that many particles are not simple spheres, but complex aggregates of smaller components. These fluffy, snowflake-like structures preserve information about the gentle processes by which the particles grew through accretion of smaller components. The delicate structures will be destroyed by violent collisions, indicating that the particles experienced relatively gentle conditions during their formation and early evolution. Some cosmic dust particles contain evidence of having been repeatedly heated and cooled, indicating that they experienced multiple passages through warm and cold regions of space. This thermal history is preserved in the crystal structure of the minerals within the particles, providing a record of the temperature variations the particles encountered during their journey. The discovery of pre-solar grains in cosmic dust has provided some of the most dramatic insights into stellar nucleosynthesis. These grains, which formed in the atmospheres of dying stars before a solar system existed, preserve the original isotopic compositions of their parent stars. By studying these grains, scientists can learn about the nuclear processes that occurred in specific stars billions of years ago. The noble gases trapped within cosmic dust particles provide another source of information about cosmic environments. These gases, which include helium, neon, argon, and xenon, can be released from particles by careful heating and analyzed to determine their isotopic compositions. The isotopic ratios of these gases reveal information about the cosmic ray exposure history of the particles and the solar wind conditions they encountered. The study of cosmic dust particles has revealed that the boundary between living and non-living matter might be less sharp than we previously thought. Some particles contain organic compounds that are remarkably similar to biological molecules, suggesting that the chemistry that leads to life might be a natural consequence of the chemical processes that occur throughout the universe. As you rest there now, breathing quietly in the gentle darkness, you might consider that the air around you contains particles that carry within them the direct chemical signatures of distant stars and ancient cosmic processes. The dust that settles on the surfaces in your home includes particles that contain organic molecules formed in the cold depths of space, diamonds created in stellar explosions, and water that might have originated in comets or asteroids billions of years ago. The remarkable diversity of cosmic dust particles means that each speck of dust that settles around you is unique, carrying its own individual story of cosmic evolution. Some particles might contain materials that formed when our galaxy was young, while others might contain evidence of more recent cosmic events. Some might carry organic compounds that are similar to the molecules that make up living things, while others might contain exotic minerals that don't exist naturally on Earth. The study of these microscopic messengers has revolutionized our understanding of the universe and our place within it. They've shown us that the cosmos is not a sterile, lifeless void, but rather a rich chemical environment where complex molecules form and evolve. They've provided direct evidence that the elements necessary for life are distributed throughout the universe, and they've given us clues about the processes that might have contributed to the origin of life on Earth. The cosmic dust particles that settle around you are part of an ongoing delivery system that has been operating for billions of years, continuously bringing new materials and new information to our planet. They represent a direct physical connection between Earth and the cosmos, a tangible link that connects you to the most distant reaches of space and the most ancient processes of cosmic evolution. The next time you see dust particles dancing in a shaft of sunlight, you might remember that some of those particles are messengers from the stars, carrying within them information about cosmic processes that occurred billions of years ago. The next time you clean the dust from your home, You might remember that you're handling materials that contain the direct chemical signatures of stellar nucleosynthesis, supernova explosions, and the organic chemistry of interstellar space. And as you continue to drift towards sleep, you might find wonder in knowing that you're surrounded by these microscopic messengers, each one carrying a unique story of cosmic evolution, each one contributing to the rich tapestry of materials that make up our world. The cosmic dust that settles around you is not just matter. It's information, it's history, it's a direct connection to the vast and beautiful universe that is your home. The messages carried by cosmic dust remind us that we are not isolated on our small planet, but rather that we are part of a vast network of cosmic communication, receiving daily deliveries of information from the far reaches of space and time. These microscopic messengers connect us to the deepest processes of cosmic evolution, reminding us that we are made of star stuff and that our planet is constantly receiving gifts from the cosmos. In the gentle settling of cosmic dust around you, the universe is constantly sharing its secrets, its history, and its chemistry. Each particle is a small piece of the cosmic puzzle, contributing to our understanding of how the universe works and how we came to be part of it. And in this ongoing process of cosmic communication, you are not just a passive recipient, but an active participant in the grand story of cosmic evolution. Now, as you rest there with an understanding of the remarkable messages carried by cosmic dust, let me take you on a journey through the intimate process of how these cosmic materials become woven into the fabric of our planet's own story. This is where the ancient meets the immediate, where materials forged in distant stars billions of years ago join with the clay beneath your feet, the water in your glass, and the very air you breathe. It's a process of such gentle thoroughness that cosmic dust becomes not just a visitor to our world, but an integral part of Earth's ongoing evolution. Picture, if you will, a single grain of cosmic dust settling onto the rich, dark soil of a forest floor. This particle, having traveled perhaps millions of years through space, now encounters the complex chemistry of Earth's biosphere for the first time. The soil into which it settles is alive with activity. Bacteria, fungi, earthworms, and countless other organisms are constantly processing organic matter, breaking down dead leaves and roots, and cycling nutrients through the ecosystem. The cosmic dust particle, with its unique isotopic signature and its cargo of exotic organic compounds, begins to interact with this terrestrial environment. The slightly acidic conditions of the forest soil cause some of the particle's mineral components to begin dissolving, releasing elements that were forged in the heart of a distant star into the soil solution, where they can be taken up by plant roots. A nearby oak tree, its roots extending deep into the soil, begins to absorb these cosmic elements along with the terrestrial nutrients it needs for growth. The iron that was created in a supernova explosion billions of years ago becomes part of the chlorophyll molecules in the tree's leaves. The carbon that formed in the cold depths of interstellar space becomes incorporated into the cellulose that gives the tree its structure. The trace elements that bear the isotopic signatures of ancient stellar processes become part of the tree's metabolism. As the seasons change, the leaves of the oak tree fall to the forest floor, carrying with them the cosmic elements that the tree absorbed from the soil. The leaves decompose, releasing these elements back into the soil, where they can be taken up by other plants or transported by groundwater to nearby streams and rivers. In this way, the cosmic dust particle becomes part of the continuous cycling of materials through the forest ecosystem. But the integration of cosmic dust into Earth systems extends far beyond individual particles settling onto forest floors. The process occurs on a global scale, with cosmic dust becoming mixed into every major reservoir of materials on our planet. The atmosphere, the oceans, the continents, the polar ice caps, all of these contain significant contributions from cosmic dust accumulated over billions of years. In the atmosphere, cosmic dust particles serve as nucleation sites for the formation of water droplets and ice crystals. As water vapor condenses around these particles, it creates clouds that contain a mixture of terrestrial and cosmic materials. When these clouds produce precipitation, the raindrops and snowflakes that fall carry cosmic dust particles to the surface, distributing cosmic materials across the landscape. The rainwater that flows from these precipitation events carries dissolved elements from cosmic dust particles into rivers and streams. These waterways transport cosmic materials from the continents to the oceans, where they become part of the marine environment. The mixing is so thorough that it's impossible to find any body of water on Earth that doesn't contain some contribution from cosmic sources. In the oceans, cosmic dust particles settle through the water column, eventually reaching the seafloor, where they become incorporated into marine sediments. These sediments, which accumulate at rates of just a few inches per 1,000 years, preserve a detailed record of cosmic dust deposition throughout Earth's history. By studying deep-sea sediment cores, scientists can reconstruct how the rate of cosmic dust accumulation has changed over millions of years. The marine organisms that live in the oceans also interact with cosmic dust particles. Microscopic plankton can incorporate cosmic dust into their cellular structures, and when these organisms die, they sink to the ocean floor, carrying cosmic materials with them. Larger marine animals that feed on plankton ingest cosmic dust particles along with their food, and these particles become part of the marine food web. The integration of cosmic dust into oceanic systems is particularly thorough because the oceans are constantly mixing. The great ocean currents that circulate around the globe carry cosmic materials from one ocean basin to another, while the vertical mixing caused by temperature differences and the actions of marine life carry cosmic dust particles from the surface to the deep ocean and back again. On land, the integration of cosmic dust into terrestrial systems occurs through multiple pathways. The particles that settle directly onto soil surfaces become part of the complex mixture of organic and inorganic materials that make up the soil. The particles that are washed from the atmosphere by precipitation join the hydrological cycle, being transported by rivers and streams to lakes and oceans. The biological uptake of cosmic materials is particularly fascinating. Plants absorb elements from cosmic dust particles through their roots, and these elements become part of the plant's structure and metabolism. When animals eat these plants, the cosmic elements become part of the animal's body. When the animals die and decompose, the cosmic elements are released back into the environment, where they can be taken up by other organisms. This biological cycling of cosmic materials means that every living thing on Earth contains elements that originated in cosmic dust. The carbon in your body includes atoms that were once part of cosmic dust particles. The iron in your blood includes atoms that were created in stellar explosions and delivered to Earth by cosmic dust. The calcium in your bones, the phosphorus in your DNA, the trace elements that are essential for your metabolism. All of these include contributions from cosmic sources. The integration of cosmic dust into Earth systems is not just a matter of mixing different materials together. It's also a process of chemical transformation, where the exotic compounds and minerals in cosmic dust particles undergo reactions with terrestrial materials to create new substances that wouldn't exist without this cosmic contribution. For example, the organic compounds in cosmic dust particles can react with organic matter in soil to create new types of humic substances, the complex organic molecules that give soil its dark color and its ability to retain nutrients. These humic substances are essential for soil fertility, and their properties are influenced by the cosmic organic compounds that have been incorporated into them over millions of years. The mineral components of cosmic dust particles also undergo chemical transformations as they interact with Earth's environment. The exotic minerals that formed in stellar atmospheres or supernova explosions can react with terrestrial minerals to create new compounds with unique properties. These reactions contribute to the chemical diversity of Earth's crust and may have played a role in the development of some of the mineral deposits that are economically important today. The isotopic signatures of cosmic dust particles become mixed with terrestrial isotopic signatures through these chemical reactions. Over time, this mixing has created the isotopic compositions that we observe in Earth's rocks, oceans, and atmosphere today. The cosmic contribution to these isotopic signatures provides information about the sources and processes that contributed to Earth's formation and early evolution. The integration of cosmic dust into Earth's climate system is particularly important. The particles that settle onto ice sheets and glaciers become trapped in the ice, where they can influence the ice's optical properties and its response to solar radiation. Dark particles in ice can absorb sunlight and accelerate melting, while other particles can serve as nucleation sites for the formation of ice crystals. The cosmic dust particles that settle onto snow and ice also preserve a record of past cosmic dust deposition that can be studied by analyzing ice cores. These ice cores contain layers that correspond to different time periods, and the cosmic dust content of these layers provides information about how cosmic dust deposition has varied over thousands of years. The integration of cosmic dust into Earth's magnetic field is another fascinating aspect of this process. Some cosmic dust particles contain magnetic minerals that can interact with Earth's magnetic field. When these particles settle onto the surface, they can become aligned with the local magnetic field direction, preserving a record of the magnetic field's orientation at the time of deposition. The study of cosmic dust particles in sedimentary rocks has provided insights into the history of Earth's magnetic field and how it has changed over geological time. The magnetic orientations preserved in cosmic dust particles can be used to track the movement of continents and the evolution of Earth's magnetic field over millions of years. The integration of cosmic dust into Earth systems has also influenced the evolution of life on our planet. The organic compounds delivered by cosmic dust may have provided some of the raw materials for the origin of life. The trace elements in cosmic dust particles may have been essential nutrients for early life forms. The isotopic signatures of cosmic dust may have influenced the isotopic compositions of biological molecules. Some scientists have proposed that cosmic dust particles may have served as templates or catalysts for the formation of the first biological molecules. The surfaces of cosmic dust particles could have provided sites where simple organic molecules could come together and react to form more complex structures. The unique chemical environments created by cosmic dust particles might have facilitated chemical reactions that wouldn't have occurred otherwise. The ongoing delivery of cosmic dust to Earth continues to influence biological processes today. The nutrients delivered by cosmic dust particles contribute to the productivity of ecosystems, particularly in remote areas where terrestrial sources of nutrients are limited. The organic compounds in cosmic dust particles may serve as food sources for certain types of microorganisms. The integration of cosmic dust into human-modified environments is also worth considering. The cosmic dust particles that settle onto agricultural fields become part of the soil that grows our food. The particles that settle onto urban areas become part of the dust that we encounter in our daily lives. The particles that settle onto water supplies become part of the water that we drink. The construction materials that we use to build our homes and cities contain cosmic dust particles that have been incorporated into the raw materials from which these materials are made. The concrete, the steel, the glass, the wood, all of these contain cosmic contributions that have been mixed into terrestrial materials over millions of years. The integration of cosmic dust into Earth systems is so thorough that it's impossible to find any part of our planet that doesn't contain cosmic contributions. The rocks beneath your feet, the air you breathe, the water you drink, the food you eat, all of these contain elements and compounds that originated in cosmic dust particles. This integration is not just a historical process that occurred in the past. It's an ongoing process that continues today. As you rest there now, cosmic dust particles are settling around you and beginning their integration into Earth systems. Some particles are landing on soil where they'll be taken up by plants. Others are landing on water where they'll become part of the hydrological cycle. Still others are landing on surfaces where they'll be incorporated into the dust that circulates through human environments. The remarkable thing about this integration process is how it connects the cosmic and the terrestrial in ways that are both profound and intimate. The cosmic dust that settles around you doesn't remain separate from Earth systems. It becomes part of them, contributing to the chemical complexity and diversity that make our planet such a remarkable place. As you breathe quietly now, you might consider that the oxygen entering your lungs includes atoms that were once part of cosmic dust particles. The water in your body includes molecules that may have originated in comets or asteroids. The food you ate today contains elements that were delivered to Earth by cosmic dust and then taken up by plants and animals through the natural processes of nutrient cycling. This integration of cosmic and terrestrial materials creates a planet that is constantly being renewed and enriched by contributions from space. Earth is not a closed system. It's an open system that is constantly receiving new materials and new information from the cosmos. The cosmic dust that settles around you is part of this ongoing process of cosmic enrichment. The next time you see soil in a garden or a forest, you might remember that it contains cosmic dust particles that have been incorporated into the complex mixture of materials that supports plant life. The next time you drink a glass of water, you might remember that it contains dissolved elements that originated in cosmic dust particles. The next time you take a deep breath, you might remember that you're breathing air that contains particles that have traveled from the far reaches of space. And as you continue to drift towards sleep, you might find wonder in knowing that you are part of this ongoing process of cosmic integration, that your body contains elements that were delivered to Earth by cosmic dust, and that the planet you live on is constantly being enriched by contributions from the cosmos. The mixing of cosmic and terrestrial materials that we've explored in this chapter is not just a geological process. It's a process that connects you directly to the universe beyond our planet. The integration of cosmic dust into Earth's story is one of the most beautiful examples of how the universe works as a connected whole, where materials and energy flow freely between different environments and different scales. In this process, the ancient and the immediate, the cosmic and the terrestrial, the distant and the intimate all become part of a single, unified story of which you are an integral part. Now, as you rest there with an understanding of how cosmic dust becomes woven into Earth's systems, let me take you on a gentle journey to the vast blue expanses of our planet's oceans, where the most remarkable collection of cosmic dust has been quietly accumulating for billions of years. The oceans serve as Earth's greatest repository of cosmic materials, a liquid library where the history of our solar system and galaxy has been carefully preserved in layers of sediment that stretch back through deep time. Picture, if you will, the surface of the Pacific Ocean on a calm evening, the water so still that it mirrors the star-filled sky above. The boundary between ocean and atmosphere is almost invisible, a subtle interface where cosmic dust particles make their transition from their long journey through space to their final resting place in the deep ocean basins. Each particle that touches the surface of the water begins a new chapter in its story, one that will carry it through the complex marine environment to the seafloor below. As a cosmic dust particle settles onto the ocean's surface, it encounters an environment unlike anywhere else on Earth. The seawater, with its complex chemistry of dissolved salts and organic compounds, immediately begins to interact with the particle. If the particle contains water-soluble minerals, these begin to dissolve, releasing elements that were forged in distant stars into the marine environment where they can be taken up by marine organisms. The particle's journey through the water column is a gentle descent that can take days, weeks, or even months, depending on the particle's size and the ocean circulation patterns. As it sinks, the particle encounters the layered structure of the ocean, the warm, sunlit surface waters where phytoplankton photosynthesize, the deeper waters where temperatures drop and pressure increases, and finally the cold, dark depths where strange creatures have evolved to live in eternal night. During this descent, the cosmic dust particle becomes part of the marine ecosystem in ways both subtle and profound. Microscopic marine organisms called phytoplankton, which form the base of the ocean's food web, can incorporate cosmic dust particles into their cellular structures. These tiny organisms, each one smaller than the width of a human hair, are constantly filtering particles from the seawater as they feed and grow. When a phytoplankton cell incorporates a cosmic dust particle, that particle becomes part of the marine food web. The phytoplankton might be eaten by tiny zooplankton, which in turn might be eaten by small fish, which might be eaten by larger fish, and so on up the food chain. In this way, cosmic dust particles become distributed throughout the marine ecosystem, contributing their unique chemistry to the tissues of marine organisms. The cosmic dust particles that aren't consumed by marine life continue their slow descent toward the seafloor. As they sink, they encounter the marine snow, a constant gentle precipitation of organic particles that drift down from the surface waters. This marine snow consists of dead phytoplankton, fecal pellets from marine animals, and other organic debris that slowly settles toward the bottom. The cosmic dust particles become incorporated into this marine snow, joining the organic materials in their journey to the deep ocean floor. This process aggregates the cosmic particles with terrestrial organic matter, creating composite particles that carry both cosmic and terrestrial materials to the seafloor. The gentle mixing of cosmic and terrestrial materials that occurs in marine snow is one of the most intimate examples of how our planet integrates cosmic contributions into its own systems. When these mixed particles finally reach the seafloor, they join the sediments that are slowly accumulating in the deep ocean basins. These sediments, which build up at rates of just a few inches per thousand years, create a detailed record of cosmic dust deposition that stretches back hundreds of millions of years. Each layer of sediment represents a snapshot of the cosmic dust that was falling to Earth at a particular time in the past. The deep ocean sediments are like pages in a book that tells the story of our solar system's history. By studying sediment cores taken from different parts of the ocean floor, scientists can reconstruct how the rate of cosmic dust accumulation has varied over geological time. They can identify periods when the solar system passed through dense regions of cosmic dust, and they can correlate these periods with other events in Earth's history. The cosmic dust preserved in ocean sediments has revealed some remarkable discoveries about our planet's past. Scientists have found evidence of ancient supernova explosions preserved in the isotopic signatures of cosmic dust particles. They've identified periods when large asteroids or comets broke apart in the inner solar system, creating temporary increases in cosmic dust deposition. They've even found evidence of cosmic dust from outside our solar system, particles that originated in other star systems and traveled through interstellar space to reach Earth. The abyssal plains of the deep ocean, those vast flat regions that cover much of the ocean floor, are particularly rich in cosmic dust. These areas, far from the continental margins where terrestrial sediments dominate, receive relatively pure cosmic dust that hasn't been mixed with large amounts of terrestrial material. The sediments in these regions can be up to 30% cosmic dust by weight, making them some of the most concentrated repositories of cosmic material on Earth. The mid-ocean ridges, where new oceanic crust is formed as tectonic plates spread apart, create unique environments for cosmic dust deposition. The volcanic activity at these ridges releases hot, mineral-rich water that can react with cosmic dust particles, creating new types of minerals that don't exist elsewhere on Earth. The hydrothermal vents at these ridges support unique ecosystems where cosmic dust particles can become incorporated into the tissues of organisms that live nowhere else. The deep ocean trenches, where oceanic crust is subducted back into the Earth's mantle, represent the final destination for much of the cosmic dust that accumulates on the ocean floor. As the oceanic crust, carrying cosmic dust-rich sediments, is drawn down into the mantle, the cosmic materials are recycled back into the Earth's interior, where they can eventually be returned to the surface through volcanic activity. This recycling of cosmic dust through the Earth's interior is part of the plate tectonic cycle that has been operating for billions of years. The cosmic dust that settles onto the ocean floor today may eventually be subducted into the mantle, where it will be heated and partially melted. Some of this material may be returned to the surface in volcanic eruptions, bringing cosmic elements back into the atmosphere and hydrosphere, where they can once again become part of the surface environment. The ocean's cosmic collection is not just a passive repository of cosmic materials. It's an active system where cosmic dust particles continue to interact with marine chemistry and biology. The dissolved elements released by cosmic dust particles become part of the ocean's chemical inventory, influencing the chemistry of seawater and the organisms that live in it. The trace elements delivered by cosmic dust particles are particularly important for marine life. Elements like iron, which is essential for photosynthesis and phytoplankton, are delivered to the oceans in significant quantities by cosmic dust. In some parts of the ocean, particularly in remote areas far from terrestrial sources of nutrients, cosmic dust may be the primary source of certain essential elements for marine life. The organic compounds in cosmic dust particles also contribute to the ocean's organic chemistry. These compounds, which include amino acids and other complex molecules, can serve as nutrients for marine microorganisms. Some scientists have proposed that cosmic dust particles may have been an important source of organic compounds for the earliest life forms that evolved in the oceans billions of years ago. The seasonal and regional variations in cosmic dust deposition create patterns in the ocean's cosmic collection that reflect the complex dynamics of our solar system. During certain times of year, when Earth passes through the debris trails of comets, the rate of cosmic dust deposition increases. During other times, when Earth is relatively isolated from major cosmic dust sources, the deposition rate decreases. These variations are preserved in the ocean sediments, creating annual layers that can be counted like tree rings to determine the age of different sediment layers. The cosmic dust content of these layers provides information about how cosmic dust deposition has varied over time, and it can be correlated with other environmental changes to understand how cosmic dust influences Earth's climate and ecosystems. The polar regions of the ocean play a special role in cosmic dust collection because of their unique environmental conditions. The cold waters of the Arctic and Antarctic oceans can preserve cosmic dust particles in better condition than warmer waters, and the seasonal formation of sea ice can concentrate cosmic dust particles in ways that create particularly rich deposits. The ice sheets that surround the polar oceans also contribute to cosmic dust collection by trapping particles that fall onto the ice surface. When this ice melts, either seasonally or over longer time periods, it releases cosmic dust particles into the ocean water, creating pulses of cosmic dust deposition that can be preserved in the sedimentary record. The deep ocean currents that circulate around the globe carry cosmic dust particles from one ocean basin to another, creating a global mixing system that distributes cosmic materials throughout the world's oceans. The thermohaline circulation, driven by differences in temperature and salinity, carries cosmic dust particles from the surface waters where they enter the ocean down to the deep waters where they can remain for hundreds or thousands of years. The upwelling of deep waters in certain regions brings cosmic dust particles back to the surface, where they can once again become part of the surface ocean ecosystem. This vertical mixing of the oceans ensures that cosmic dust particles are distributed throughout the water column, from the surface to the deepest depths. The interaction between cosmic dust and marine life creates complex feedback loops that influence both the preservation of cosmic materials and the evolution of marine ecosystems. Marine organisms that incorporate cosmic dust particles into their shells or skeletons can concentrate cosmic materials in ways that make them easier to study. When these organisms die, their shells sink to the seafloor, carrying cosmic dust particles with them in a concentrated form. The bioluminescent organisms that live in the deep ocean, those creatures that create their own light through biochemical processes, may be indirectly dependent on cosmic dust for some of the trace elements they need for their light-producing reactions. The cosmic dust that settles into the deep ocean provides a continuous supply of these elements, supporting the remarkable light displays that occur in the ocean's depths. The coral reefs that grow in tropical oceans also interact with cosmic dust in interesting ways. The coral polyps that build these reefs can incorporate cosmic dust particles into their calcium carbonate skeletons, creating a record of cosmic dust deposition that can be studied by analyzing coral cores. The growth rings in coral skeletons can be counted to determine their age, and the cosmic dust content of these rings provides information about how cosmic dust deposition has varied over the coral's lifetime. The great ocean gyres, those circular current systems that dominate the circulation of each ocean basin, create regions where cosmic dust particles can accumulate in particularly high concentrations. The center of these gyres, where the water moves slowly and particles tend to sink, can become collection points for cosmic dust that creates some of the richest deposits of cosmic material in the oceans. The ocean's cosmic collection represents one of the most complete and continuous records of cosmic dust deposition available anywhere on Earth. Unlike terrestrial deposits, which can be eroded or disturbed by geological processes, the deep ocean sediments provide a relatively undisturbed record of cosmic dust accumulation that can extend back hundreds of millions of years. As you rest there now, breathing quietly in the gentle darkness, you might imagine the vast blue expanses of the world's oceans, quietly collecting cosmic dust in their depths. Every day, cosmic dust particles are settling onto the ocean's surface and beginning their journey to the seafloor. Some of these particles are being incorporated into the tissues of marine organisms, while others are joining the sediments that preserve the record of cosmic dust deposition. The oceans that cover more than 70% of our planet's surface are not just bodies of water. They're cosmic collectors, gathering and preserving the materials that the universe has been sending to Earth for billions of years. The water that makes up these oceans contains dissolved elements that originated in cosmic dust particles. The sediments that cover the ocean floor contain the concentrated remains of cosmic dust that has been accumulating for geological ages. The marine life that inhabits these oceans has evolved in an environment that has been continuously enriched by cosmic dust. The phytoplankton that form the base of the marine food web, the fish that swim in the open ocean, the whales that migrate across ocean basins. All of these creatures contain elements that were delivered to Earth by cosmic dust and then incorporated into the ocean's chemical inventory. The next time you see the ocean, whether from a beach, a cliff, or even from an airplane, you might remember that beneath those waves lies one of the most remarkable collections of cosmic material anywhere on Earth. The next time you eat seafood, you might remember that the fish or shellfish you're eating contains elements that were delivered to the ocean by cosmic dust. The next time you drink water, you might remember that some of the dissolved minerals in that water may have originated in cosmic dust particles. And as you continue to drift towards sleep, you might find peace in knowing that the oceans of our planet are constantly receiving and preserving the cosmic gifts that fall from space. The ocean's cosmic collection is not just a scientific curiosity. It's a testament to the profound connections that exist between Earth and the cosmos. A reminder that our planet is not isolated in space, but is part of a vast network of material and energy exchange that spans the entire universe. The gentle accumulation of cosmic dust in the ocean depths is one of the most patient and persistent processes occurring on our planet. It connects the immediate present, as particles settle onto the ocean's surface today, with a deep past, as ancient cosmic materials are preserved in sediments that formed millions of years ago. It connects the local, as particles settle into specific ocean basins, with the global, as ocean currents distribute cosmic materials around the world. And it connects the cosmic with the terrestrial, as materials from distant stars become part of the Earth's own story. Now, as you rest there with an understanding of how cosmic dust accumulates in our planet's great ocean basins, let me take you on the most intimate journey of all, the path that cosmic dust takes as it becomes part of your own body, your own breath, your own life. This is where the cosmic and the personal meet, where materials that began their journey in the hearts of distant stars find their way into the very molecules that make up your cells, your tissues, and your consciousness. Take a slow, deep breath now. And as you do, consider that the air filling your lungs contains particles that have traveled across the galaxy to reach this moment. The cosmic dust that we've been following on its journey from space to ocean is also present in the atmosphere around you, suspended in the air you breathe, waiting to become part of your body's own story. The cosmic dust particles in the air around you are incredibly small, so small that they can pass through the filters and barriers that protect your respiratory system from larger particles. When you inhale, these microscopic visitors enter your nose or mouth along with the oxygen and other gases that your body needs to survive. They travel through your respiratory system, past your throat, and down into your lungs, where they encounter the delicate tissues that extract oxygen from the air. In your lungs, the cosmic dust particles encounter the alveoli, those tiny air sacs where gas exchange occurs between the air and your bloodstream. The walls of the alveoli are incredibly thin, designed to allow oxygen molecules to pass easily from the air into your blood. Some cosmic dust particles are so small that they can pass through these walls as well, entering your bloodstream and beginning a journey through your circulatory system. Once in your bloodstream, cosmic dust particles become part of the complex fluid that carries nutrients, oxygen, and other essential substances throughout your body. The blood that flows through your arteries and veins carries these cosmic visitors to every organ, every tissue, every cell in your body. In this way, cosmic dust particles become distributed throughout your entire organism, contributing their unique chemistry to the biological processes that keep you alive. The iron in your blood, which is essential for carrying oxygen from your lungs to your tissues, includes atoms that were created in the nuclear furnaces of ancient stars and delivered to Earth by cosmic dust. These iron atoms, forged in stellar cores billions of years ago, now serve one of the most fundamental functions in your body, enabling your cells to receive the oxygen they need to generate energy. The calcium in your bones, which provides the structural framework that supports your body, also includes contributions from cosmic dust. As calcium from cosmic dust particles is absorbed into your bloodstream, it can be incorporated into the ongoing process of bone formation and maintenance. The skeleton that supports you as you rest there now contains atoms that once drifted through the cold vacuum of space. The carbon atoms that make up the organic molecules in your cells, the proteins, the DNA, the carbohydrates, and the fats, include atoms that were delivered to Earth by cosmic dust. These carbon atoms, created in the hearts of dying stars, now participate in the complex chemistry of life, forming the molecular structures that enable your cells to function, reproduce, and maintain themselves. The trace elements that are essential for your body's biochemistry, elements like zinc, copper, selenium, and others, are present in cosmic dust particles and become part of your body's chemical inventory as you breathe, eat, and drink. These elements, though needed in only tiny amounts, are crucial for the proper functioning of enzymes, hormones, and other biological molecules. The process by which cosmic dust becomes part of your body is remarkably gentle and gradual. Unlike the dramatic entry of cosmic dust into Earth's atmosphere, the integration of cosmic dust into your body occurs through the same natural processes that bring all nutrients and materials into your system. You don't feel the cosmic dust particles entering your body, and you're not aware of their integration into your tissues, but the process is constant and ongoing. When you eat food, you're consuming plants and animals that have themselves incorporated cosmic dust into their tissues. The vegetables you eat have taken up elements from cosmic dust particles through their roots. The meat you eat comes from animals that breathe cosmic dust particles and ate plants that contain cosmic elements. In this way, cosmic dust enters your body not just through your lungs, but through your entire digestive system. The water you drink also contains dissolved elements that originated in cosmic dust particles. As cosmic dust settles onto the surface of reservoirs, rivers, and groundwater sources, it slowly dissolves, releasing its constituent elements into the water supply. When you drink this water, you're consuming cosmic elements that become part of your body's fluid balance and cellular chemistry. The process of cosmic dust integration into your body is so thorough that it's impossible to identify any part of your body that doesn't contain cosmic contributions. Your brain, with its billions of neurons and complex network of connections, contains atoms that were forged in stellar cores. Your heart, which beats steadily throughout your life, contains cosmic elements that participate in the electrical and chemical processes that coordinate its rhythm. Your muscles, which enable you to move and maintain your posture, contain cosmic atoms that participate in the contraction and relaxation cycles that produce movement. Your skin, which protects you from the environment and helps regulate your body temperature, contains cosmic elements that are part of the complex proteins and other molecules that make up your body's largest organ. The cosmic dust that becomes part of your body doesn't remain unchanged. Once incorporated into your tissues, the cosmic atoms participate in the ongoing chemical processes that maintain your body's function. They become part of the continuous cycle of molecule breakdown and synthesis that characterizes all living systems. The proteins in your body are constantly being broken down and rebuilt, and cosmic atoms participate in this process. The DNA in your cells, which contains the genetic instructions that guide your body's development and function, may contain cosmic carbon atoms that become part of the double helix structure that stores your genetic information. The cosmic dust that you breathe today may become part of proteins that are synthesized tomorrow, or it may become incorporated into cellular structures that will remain part of your body for months or years. The turnover of different tissues in your body occurs at different rates, so cosmic atoms may remain in some parts of your body longer than others. The cosmic dust integration into your body is not just a physical process. It's also connected to the energy systems that power your life. The cosmic atoms that become part of your body can participate in the biochemical reactions that generate the energy your cells need to function. They can become part of the electron transport chains that produce ADP, the molecule that serves as the primary energy currency of your cells. The cosmic organic compounds that are present in some cosmic dust particles may serve as raw materials for the synthesis of biological molecules in your body. The amino acids found in cosmic dust, for example, could potentially be incorporated into the proteins that your body synthesizes. The organic compounds could also serve as sources of carbon for the synthesis of other organic molecules that your body needs. The integration of cosmic dust into your body also connects you to the broader ecosystem of life on Earth. The cosmic atoms that become part of your body will eventually be returned to the environment when your body breaks down organic molecules for energy or when tissues are renewed. In this way, cosmic atoms cycle through your body and then back into the environment, where they can become part of other living systems. The cosmic dust that you breathe out when you exhale may carry with it some of the cosmic atoms that were temporarily part of your body. These atoms, now expelled back into the atmosphere, can be breathed by other organisms or can settle back onto the Earth's surface, where they can become part of other ecosystems. The process of cosmic dust integration into your body is also connected to the larger cycles of matter and energy that characterize life on Earth. The cosmic atoms that become part of your body are part of the same cycles that move carbon, nitrogen, phosphorus, and other elements through the biosphere. They participate in the same processes that connect all living things in a web of chemical relationships. The cosmic dust that becomes part of your body also connects you to the deep history of the universe. The atoms that are now part of your tissues were created in stellar cores that lived and died billions of years ago. They have traveled through interstellar space, been incorporated into the solar nebula from which our solar system formed, and eventually found their way to Earth and into your body. This perspective can be profoundly moving. You are not just a temporary arrangement of atoms. You are a temporary arrangement of atoms that have been on an extraordinary journey through space and time. The cosmic dust that becomes part of your body carries with it the history of stellar evolution, the story of how elements are created and distributed throughout the universe. The breathing of cosmic dust also connects you to all other life on Earth. Every living thing on our planet breathes the same atmosphere, drinks from the same water sources, and eats food that has been grown in soil enriched by cosmic dust. The cosmic atoms that become part of your body have been part of countless other organisms throughout Earth's history, and they will become part of countless other organisms in the future. The plants that produce the oxygen you breathe have incorporated cosmic dust into their tissues through the same processes that bring cosmic dust into your body. The animals that you may eat have breathed cosmic dust and incorporated it into their tissues. The decomposers that break down organic matter and return nutrients to the soil have processed cosmic dust and made it available for uptake by new generations of organisms. The cosmic dust that you breathe connects you not just to the universe beyond Earth, but to the community of life on our planet. It's a reminder that all living things are connected by the same fundamental processes, the same chemical cycles, the same flow of matter and energy through the biosphere. As you rest there now, breathing quietly and peacefully, You might imagine the cosmic dust particles that are entering your body with each breath. These particles, having traveled perhaps millions of years through space, are now becoming part of your own personal story. They're joining the complex chemistry that maintains your life, contributing their unique atomic signatures to the ongoing process of your existence. The cosmic dust that you breathe today may become part of the proteins that repair your muscles tonight, or part of the neurotransmitters that carry signals between your brain cells tomorrow. It may become part of the hemoglobin that carries oxygen through your bloodstream, or part of the enzymes that catalyze the chemical reactions that power your cells. The remarkable thing about breathing cosmic dust is that it's completely natural and unconscious. You don't have to think about it or make any effort to incorporate cosmic materials into your body. It happens automatically as part of the same biological processes that have been sustaining life on Earth for billions of years. The cosmic dust that becomes part of your body is also part of the same ongoing process that has been connecting Earth to the cosmos throughout our planet's history. The first life forms that evolved on Earth billions of years ago were breathing the same cosmic dust that you breathe today. The dinosaurs that lived hundreds of millions of years ago incorporated cosmic dust into their tissues. Every human being who has ever lived has breathed cosmic dust and made it part of their body. This continuity across time is one of the most beautiful aspects of cosmic dust integration. You are part of an unbroken chain of life that has been incorporating cosmic materials for billions of years. The cosmic dust that becomes part of your body connects you not just to the stars, but to all of life's history on Earth. The cosmic dust that you breathe also connects you to the future. The cosmic atoms that become part of your body today will eventually be returned to the environment, where they can become part of future ecosystems and future life forms. In this way, you are not just a recipient of cosmic dust. You are also a participant in the ongoing process of cosmic dust integration that will continue long after your individual lifetime. As you continue to breathe slowly and peacefully, you might find comfort in knowing that you are part of this vast, ongoing process of cosmic integration. Every breath you take brings cosmic materials into your body, making you a direct participant in the grand story of how the universe creates and distributes the elements that make life possible. The next time you take a deep breath of fresh air, you might remember that you're breathing atoms that were forged in the hearts of ancient stars. The next time you feel your heart beating, you might remember that it's powered by cosmic elements that have traveled across the galaxy to become part of your body. The next time you move your muscles or think a thought, you might remember that cosmic atoms are participating in the chemical processes that make these activities possible. And as you drift towards sleep, you might find peace in knowing that you are made of star stuff in the most literal sense. Not just because the elements in your body were created in stars, but because those elements are continuously being delivered to Earth by cosmic dust and continuously being incorporated into your body through the simple act of breathing. In every breath, you are renewing your connection to the cosmos, making yourself part of the ongoing story of how the universe shares its materials with the life that has evolved on our remarkable planet. Now, as you rest there with an understanding of how cosmic dust becomes part of your own body, let me take you on a journey through the vast scales of time over which cosmic dust has been slowly but steadily transforming our planet. This is the story of how billions of years of gentle cosmic rain have gradually changed the composition of Earth's atmosphere, oceans, and continents, creating the chemical complexity that makes our world such a remarkable place for life to flourish. Picture, if you will, the Earth as it was 4 billion years ago, a young planet still glowing with the heat of its formation, its surface covered with molten rock, and its atmosphere filled with volcanic gases. This early Earth was a very different world from the one we know today, with an atmosphere that contained no oxygen, oceans that were just beginning to form, and a surface that was constantly being reshaped by impacts from asteroids and comets. Even in those ancient times, cosmic dust was falling onto our planet, beginning the slow process of transformation that would eventually create the world we inhabit today. The cosmic dust that settled onto the early Earth brought with it elements and compounds that weren't present in the original materials from which our planet formed. These cosmic contributions, tiny as they were on a daily basis, began to accumulate and influence the chemistry of our planet's surface. The early atmosphere of Earth contained virtually no oxygen, consisting instead mainly of carbon dioxide, nitrogen, and various volcanic gases. The cosmic dust that fell through this ancient atmosphere brought with it trace amounts of elements that would eventually become crucial for life. Elements like iron, which would later become essential for photosynthesis, and organic compounds that would contribute to the complex chemistry from which life would emerge. As the eons passed, the cosmic dust continued to accumulate, gradually changing the chemical composition of Earth's surface materials. The iron delivered by cosmic dust became incorporated into the rocks and minerals that were forming on the planet's surface. The organic compounds in cosmic dust contributed to the complex mixture of chemicals that existed in the early oceans, where life would eventually emerge. The emergence of life on Earth, which occurred roughly 3.5 billion years ago, marked a turning point in how cosmic dust influenced our planet's transformation. The first living organisms were simple bacteria that lived in the oceans and obtained their energy from chemical reactions rather than from sunlight. These early life forms interacted with the cosmic dust that was constantly settling into the oceans, incorporating cosmic elements into their cellular structures and participating in the ongoing chemical transformation of the planet. The development of photosynthesis, which occurred about 2.5 billion years ago, created one of the most dramatic transformations in Earth's history. Photosynthetic organisms began to produce oxygen as a waste product, gradually changing the composition of the atmosphere and creating the oxygen-rich environment that we know today. The cosmic dust that was falling onto the planet during this period contributed elements that were essential for photosynthesis, including iron and other trace elements that are crucial for the biochemical processes that convert sunlight into chemical energy. The increase in atmospheric oxygen, known as the Great Oxidation Event, had profound effects on the fate of cosmic dust particles as they entered Earth's atmosphere. The oxygen-rich atmosphere created new chemical environments where cosmic dust particles could undergo oxidation reactions, forming new types of minerals and compounds that didn't exist in the oxygen-poor atmosphere of the early Earth. The iron in cosmic dust particles, for example, began to form iron oxides when it encountered the oxygen in the atmosphere. These iron oxides gave the cosmic dust particles different physical and chemical properties, affecting how they interacted with other materials in the environment. The formation of iron oxides also contributed to the reddish coloration that characterizes many of the sedimentary rocks that formed during this period. The evolution of more complex life forms over the following billions of years created new pathways for cosmic dust to influence Earth's transformation. Plants, which evolved about 500 million years ago, began to actively take up cosmic elements from the soil through their roots. The cosmic dust that had been accumulating in soils for billions of years suddenly became available to living organisms in new ways, contributing to the complex chemistry of plant tissues and the ecosystems that plants supported. The development of forests created new mechanisms for cosmic dust collection and transformation. The leaves of trees provided vast surface areas for cosmic dust to settle onto, and the root systems of forests extended deep into the soil, accessing cosmic elements that had been accumulating for millions of years. When trees died and decomposed, they released these cosmic elements back into the soil, where they could be taken up by new generations of plants. The evolution of animals added another layer of complexity to the cosmic dust transformation process. Animals that ate plants consumed cosmic elements that the plants had taken up from the soil. Herbivorous animals concentrated these cosmic elements in their tissues, and carnivorous animals that ate herbivores concentrated them even further. In this way, cosmic dust became part of the complex food webs that characterize terrestrial ecosystems. The development of human civilization has added new dimensions to the cosmic dust transformation process. Human activities have changed the ways that cosmic dust is distributed and concentrated on Earth's surface. Agriculture has created new pathways for cosmic dust to enter the human food supply, while industrial activities have created new ways for cosmic dust to become incorporated into manufactured materials. The slow transformation of Earth's climate over geological time has also been influenced by cosmic dust accumulation. The cosmic dust that settles onto ice sheets and glaciers becomes incorporated into the ice, where it can influence the ice's optical properties and its response to solar radiation. During ice ages, when large portions of the planet's surface were covered by ice, cosmic dust accumulated in the ice sheets, creating concentrated deposits of cosmic material that were released when the ice melted. The movement of continents due to plate tectonics has distributed cosmic dust around the globe over geological time. The cosmic dust that accumulated in one location might later be transported to a completely different part of the planet as continents drifted and collided. This continental drift has mixed cosmic dust from different time periods and different cosmic sources, creating the complex distribution of cosmic materials that we observe in Earth's rocks today. The formation of mountain ranges through tectonic processes has created new environments for cosmic dust accumulation and transformation. The high elevations of mountain ranges receive cosmic dust that has been less affected by atmospheric processing, while the erosion of mountains distributes cosmic dust-rich materials to lower elevations and to the oceans. The slow transformation of Earth's surface through weathering and erosion has continuously reworked the cosmic dust that has accumulated over billions of years. The cosmic dust that originally settled onto ancient rock surfaces has been broken down by chemical weathering, transported by rivers and glaciers, and redeposited in new locations. This ongoing reworking has distributed cosmic elements throughout Earth's surface materials. The development of soils through the weathering of rocks has created new environments where cosmic dust can accumulate and interact with biological systems. The cosmic dust that settles on soil surfaces becomes incorporated into the complex mixture of organic and inorganic materials that make up soil. The biological activity in soils, including the actions of bacteria, fungi, and other microorganisms, has created new pathways for cosmic dust to be processed and made available to plant life. The formation of sedimentary rocks from accumulated sediments has preserved the record of cosmic dust deposition throughout Earth's history. The layers of sedimentary rocks that cover much of Earth's surface contain cosmic dust that was deposited millions or billions of years ago. By studying these rock layers, scientists can reconstruct how cosmic dust deposition has varied over geological time and how it has influenced Earth's evolution. The slow transformation of Earth's magnetic field over geological time has also been influenced by cosmic dust accumulation. The magnetic minerals and cosmic dust particles have become incorporated into Earth's rocks, where they preserve records of the magnetic field's direction and strength at the time of deposition. These magnetic records have been crucial for understanding how Earth's magnetic field has changed over time and how it has influenced the planet's climate and atmospheric evolution. The gradual change in Earth's orbital parameters over hundreds of thousands of years has created cycles in cosmic dust deposition that have influenced long-term climate patterns. The Milankovitch cycles, which describe changes in Earth's orbit and axial tilt, affect how cosmic dust is distributed around the planet and how it influences the planet's energy balance. The slow transformation of Earth's atmosphere through the accumulation of cosmic dust has created the complex atmospheric chemistry that characterizes our planet today. The trace gases delivered by cosmic dust, including various organic compounds and rare elements, have contributed to the atmospheric chemistry that supports life and influences climate. The ongoing transformation of Earth's hydrosphere through cosmic dust accumulation has influenced the chemistry of the oceans and other water bodies. The dissolved elements released by cosmic dust particles have become part of the complex chemistry of seawater, influencing the organisms that live in the oceans and the chemical processes that occur in marine environments. The transformation of Earth's biosphere through cosmic dust accumulation has been one of the most profound influences on the planet's evolution. The elements and compounds delivered by cosmic dust have become essential components of biological systems, contributing to the complex chemistry that makes life possible and influencing the evolution of life forms over geological time. The slow transformation of Earth through cosmic dust accumulation is still ongoing today. The cosmic dust that is falling onto our planet at this very moment is continuing the same process that has been occurring for billions of years, gradually changing the composition of our planet's surface materials and contributing to the ongoing evolution of Earth systems. The rate of cosmic dust accumulation has varied over geological time, influenced by factors such as the solar system's passage through different regions of the galaxy and the occurrence of nearby supernova explosions. These variations in cosmic dust deposition have created periods of more rapid transformation alternating with periods of slower change. The impact of cosmic dust on Earth's transformation has been cumulative, with each day's accumulation adding to the billions of years of previous accumulation. The cosmic dust that settles onto our planet today joins the vast inventory of cosmic materials that have been accumulating since Earth formed, contributing to the ongoing chemical evolution of our planet. The slow transformation of Earth through cosmic dust accumulation has created the chemical complexity that makes our planet unique in the solar system. The diverse array of elements and compounds that cosmic dust has delivered to Earth over billions of years has contributed to the rich chemistry that supports life and drives the complex interactions between Earth's atmosphere, oceans, and continents. As you rest there now, breathing quietly in the gentle darkness, you might imagine the vast timescales over which cosmic dust has been transforming our planet. The Earth beneath you has been slowly enriched by cosmic contributions for billions of years, creating the chemical complexity that makes life possible and that continues to influence the evolution of our planet systems. The cosmic dust that is settling around you tonight is part of the same ongoing process that has been transforming Earth since its formation. Each particle that settles onto our planet's surface adds to the accumulated cosmic inventory that has been building for billions of years, contributing to the slow but steady transformation that continues to shape our world. The remarkable thing about this transformation is its gentleness and persistence. Unlike the dramatic geological events that can reshape Earth's surface in a matter of hours or days, the transformation caused by cosmic dust accumulation occurs gradually, particle by particle, over millions and billions of years. Yet the cumulative effect of this gentle process has been profound, creating the chemical diversity that characterizes our planet and contributing to the conditions that make life possible. The slow transformation of Earth through cosmic dust accumulation is a reminder that the most important changes often occur gradually and imperceptibly. The cosmic dust that settles around you each day seems insignificant. Yet over the vast timescales of geological history, this gentle process has helped create the world we know today. As you continue to drift towards sleep, you might find comfort in knowing that you are part of this ancient and ongoing process of transformation. The cosmic dust that becomes part of your body tonight joins the billions of years of cosmic contributions that have shaped our planet and made your existence possible. In breathing cosmic dust, you are participating in the same process that has been connecting Earth to the cosmos throughout our planet's history, helping to continue the slow but steady transformation that will shape our world for billions of years to come. Now, as you rest there with an understanding of how cosmic dust has transformed our planet over billions of years, let me take you on a journey through the remarkable way that Earth has preserved these cosmic memories in stone, creating a permanent record of our planet's relationship with the cosmos. In the layers of rock that form our planet's crust, in the sediments that accumulate in quiet lake beds, and in the ice that caps our polar regions, the story of cosmic dust is written in a language that scientists are only beginning to learn how to read. Picture, if you will, a quiet canyon in the southwestern United States, where millions of years of geological history are exposed in the colorful layers of sedimentary rock that rise from the canyon floor. Each layer tells a story of the conditions that existed when it was formed, the climate, the environment, the life forms that existed at that time. But hidden within these layers, invisible to the casual observer, are the cosmic dust particles that were falling from space when each layer was deposited. The cosmic dust particles that settled onto ancient lake beds and ocean floors became incorporated into the sediments that slowly accumulated over millions of years. As these sediments were buried under newer layers, they were compressed and cemented together, forming the sedimentary rocks that preserve the record of cosmic dust deposition throughout Earth's history. The cosmic dust particles, now embedded in solid rock, became permanent residents of our planet's geological record. The limestone cliffs that rise from ancient seabeds contain cosmic dust particles that settled into tropical oceans hundreds of millions of years ago. The sandstones that formed from ancient desert dunes contain cosmic dust that blew across vast arid landscapes when the climate was very different from today. The shales that formed from mud deposited in ancient river deltas contain cosmic dust that settled during periods of quiet sedimentation. Each type of rock preserves the cosmic dust in its own unique way. In limestone, the cosmic dust particles are often incorporated into the calcium carbonate minerals that make up the rock, creating an intimate mixture of terrestrial and cosmic materials. In sandstone, the cosmic dust particles are mixed with the quartz grains that were eroded from ancient mountains, creating a record of both terrestrial and cosmic processes. The volcanic rocks that form when magma erupts from deep within the Earth also contain cosmic dust, though in a different form. The cosmic dust that had accumulated on the Earth's surface was incorporated into the magma as it melted and moved through the crust. When the magma solidified into igneous rock, it preserved the cosmic dust in the crystal structure of the minerals that formed, creating a record of cosmic dust that extends back billions of years. The ice sheets that cover Antarctica and Greenland contain perhaps the most detailed and accessible record of cosmic dust deposition. As snow falls and accumulates over thousands of years, it traps cosmic dust particles in the ice, creating annual layers that can be counted like tree rings. Scientists can extract ice cores from these ice sheets and analyze the cosmic dust content of each layer, creating a detailed record of how cosmic dust deposition has varied over the past 100,000 years. The ice core records reveal fascinating patterns in cosmic dust deposition. During ice ages, when the climate was colder and drier, more cosmic dust accumulated in the ice. During warmer periods, when the climate was more humid, less cosmic dust was preserved. These variations reflect changes in atmospheric circulation patterns and in the sources of cosmic dust that were reaching Earth. The cosmic dust preserved in ice cores also reveals the effects of major cosmic events on Earth's environment. Scientists have found evidence of increased cosmic dust deposition following nearby supernova explosions, when the shock waves from these stellar explosions swept cosmic dust toward our solar system. They've also found evidence of periods when Earth passed through particularly dense regions of cosmic dust in our galaxy. The study of cosmic dust in geological materials has revolutionized our understanding of Earth's history and its relationship with the cosmos. By analyzing the isotopic compositions of cosmic dust particles preserved in rocks of different ages, scientists can reconstruct the history of stellar nucleosynthesis in our galaxy and understand how the production of elements has changed over time. The cosmic dust preserved in rocks that formed during the early history of our solar system provides direct information about the conditions that existed when the planets were forming. These ancient cosmic dust particles contain isotopic signatures that are different from anything found in younger rocks, providing evidence of the nuclear processes that were occurring in the early solar system. The organic compounds found in cosmic dust particles preserved in ancient rocks have provided insights into the early history of life on Earth. Some of these compounds are similar to the molecules that are essential for life, suggesting that cosmic dust may have contributed to the chemical inventory from which life emerged. The preservation of these organic compounds in rocks billions of years old demonstrates the stability of cosmic dust under certain geological conditions. The magnetic properties of cosmic dust particles preserved in rocks have provided information about the history of Earth's magnetic field. The magnetic minerals in cosmic dust particles become aligned with the local magnetic field when they are deposited, preserving a record of the magnetic field's direction and strength at that time. By studying the magnetic orientations of cosmic dust particles in rocks of different ages, scientists can reconstruct how Earth's magnetic field has changed over geological time. The size and composition of cosmic dust particles preserved in rocks of different ages have provided information about how the sources of cosmic dust have changed over time. During some periods in Earth's history, the cosmic dust was dominated by particles from comets, while during other periods, it was dominated by particles from asteroids or interstellar dust. These variations reflect changes in the cosmic environment around our solar system. The cosmic dust preserved in rocks also provides information about major extinction events in Earth's history. The mass extinction that occurred 66 million years ago, which eliminated the dinosaurs, coincides with a layer of rock that contains unusually high concentrations of cosmic dust. This cosmic dust may have been produced by the impact of a large asteroid or comet, providing evidence for the cosmic cause of this extinction event. The study of cosmic dust in ancient rocks has also revealed information about the early atmosphere of Earth. The cosmic dust that settled through the early atmosphere underwent chemical reactions that were different from those that occur today, reflecting the different composition of the ancient atmosphere. By studying these ancient chemical signatures, scientists can reconstruct the evolution of Earth's atmosphere over billions of years. And so we come to the gentle conclusion of our journey through the cosmic dust that connects us to the universe. Though like the particles themselves, this story never truly ends. As you rest there now, breathing slowly and peacefully, you carry with you a new understanding of the intimate connections that bind you to the cosmos, connections that are renewed with every breath you take and every beat of your heart. The cosmic dust that we've followed on its journey from the hearts of distant stars to the cells of your body represents one of the most beautiful and constant relationships in the universe. The relationship between the vast and the intimate, between the ancient and the immediate, between the cosmic and the personal. In every grain of dust that settles around you, in every particle that becomes part of your body, the universe is sharing its story with you. As you prepare to drift into sleep, you might imagine yourself floating gently through the cosmic dust that surrounds our planet, carried by the same gentle forces that have been bringing cosmic materials to Earth for billions of years. You are not falling asleep alone. You are resting in the embrace of the cosmos itself, surrounded by the ancient light of stars and the patient drift of particles that have traveled unimaginable distances to reach this moment. The cosmic dust that settles around you tonight carries with it the light of ancient stars, the chemical signatures of stellar explosions, and the organic compounds that formed in the cold depths of space. As these particles join the Earth's systems, they become part of the ongoing story of our planet's evolution, contributing to the chemical complexity that makes life possible and connecting us to the deepest processes of cosmic evolution. Your body, resting there in the gentle darkness, is itself a temporary constellation of cosmic dust particles, a brief arrangement of atoms that were forged in stellar cores and delivered to Earth by the patient process we've explored together. The iron in your blood, the calcium in your bones, the carbon in your cells, all of these elements are cosmic dust that has found its way into the most intimate aspects of your existence. The breath you take as you drift towards sleep carries with it particles that have traveled from the far reaches of the galaxy. The dreams that will soon fill your mind will be created by neural processes that depend on cosmic elements, electrical impulses that travel through neurons containing atoms that were once part of distant stars. The cosmic dust that becomes part of your body tonight will participate in the biological processes that sustain your life. Some particles will become part of proteins that repair your tissues while you sleep. Others will become part of the cellular structures that store your memories and process your thoughts. Still others will become part of the energy-producing systems that power your body's functions. In the morning, when you wake, you will exhale some of the cosmic dust that entered your body during the night, returning these particles to the atmosphere where they can become part of other systems, other cycles, other stories. The cosmic dust that you breathe out may be breathed by other organisms, or it may settle onto the ground where it will become part of the soil that nourishes plants. The cosmic dust that we've explored together is a reminder that we are not isolated beings living on a lonely planet in an empty universe. Instead, we are part of a vast, interconnected system where matter and energy flow freely between the cosmic and the terrestrial, the ancient and the modern, the distant and the immediate. We are all made of star stuff, and we are all constantly receiving new deliveries of cosmic materials that connect us to the ongoing evolution of the universe. As you rest there, feeling the gentle weight of your body supported by the earth beneath you, you might remember that the earth itself is made partly of cosmic dust, accumulated over billions of years of patient cosmic rain. The ground that supports you, the air that surrounds you, the water that flows through your body, all of these contain contributions from the cosmic dust that has been falling onto our planet throughout its history. The next time you see dust particles dancing in a shaft of sunlight, you'll remember that some of those particles have traveled from the depths of space to join that quiet dance. The next time you feel the dust that settles in your home, you'll remember that it includes visitors from distant worlds, carrying stories of stellar birth and death, of cosmic chemistry and interstellar journeys. The next time you breathe deeply of fresh air, you'll remember that you're breathing atoms that were forged in the hearts of ancient stars and delivered to Earth by the gentle process of cosmic dust accumulation. The next time you look up at the night sky, you'll remember that you are not just observing the stars. You are made of them, connected to them by the constant flow of cosmic dust that links all matter in the universe. As sleep approaches, you might find profound peace in knowing that you are part of this ancient and ongoing cosmic story. The cosmic dust that becomes part of your body tonight has been on a journey that spans billions of years and countless light years of space. It has survived the deaths of stars, the cold of interstellar space, and the gentle integration into Earth's systems, all to become part of the brief but beautiful arrangement of atoms that is you. If you've enjoyed this gentle journey through the cosmic dust that connects us to the universe, please consider subscribing to Wiispering Atom, and let me know in the comments where you are in the world as you listen to these words. Are you breathing coastal air that carries salt from ancient oceans mixed with dust from distant stars? Are you in a mountain region where the cosmic dust settles onto peaks that reach toward the sky? Wherever you are part of the same cosmic story we've explored together. But for now, simply rest. Let yourself drift into sleep like a particle of cosmic dust settling gently onto the earth, carried by forces larger than yourself, joining the eternal dance of matter and energy that connects all things. Your dreams will be cosmic dreams, filled with the memories of stars and the whispers of ancient light. Sleep well, knowing that you are made of stardust, surrounded by stardust, breathing stardust, and connected to every star in the sky through the gentle, constant rain of cosmic dust that has been falling onto our planet for billions of years. Rest peacefully in the knowledge that you are part of something vast and beautiful and eternal. The ongoing story of how the universe shares its gifts with the life that has evolved on our remarkable planet. Sweet dreams, cosmic traveler. May you drift through the night like the gentle particles we've followed together, carrying the light of ancient stars and the promise of tomorrow's cosmic rain. And may you wake refreshed, knowing that you are not just living on a planet, but that you're a part of a living planet that is constantly receiving gifts from the cosmos and sharing them with every form of life that calls Earth home. Good night, and dream of the gentle cosmic dust that connects us all to the infinite dance of the universe.